Very good morning, Zafar sir. Very good morning, sir. Jafar sir.
Sir, mute இருக்கீங்க sir.
Jafar sir. Very good morning.
Sir, good morning, sir. Good morning, sir.
Good morning. Good morning, sir. Professor Jayvel and Professor Arivanand already joined.
Good morning, sir. Good sir. Good morning.
Very good morning, sir. Very good morning, Professor.
Very good morning, sir. Yes, sir, we started, sir.
Okay, sir.
Yeah, very good morning to everyone. It is the good morning delivered from Jamal Mohamed College, Department of Physics. We are here to have an intro on the program, online faculty development program on condensed matter physics. Actually, it is organized by the Department of Physics and the internal quality assurance cell of Jamal Mohamed College in collaboration with the ISPA, the renowned Indian Spectrophysics Association, Chennai, under the aegis of Sir Dr. S. Gunasekaran sir. We are proud to have this program. Actually, we have undergone an MOU, Memorandum of Understanding with ISPA, and in continuation with that, we are having this program, and it is run for the DBT Star College Scheme program, Department of Biotechnology Star College Scheme program, and we are having renowned persons like 4 members we are having. Dr. S. Gunasekaran, the TANSA awardee, Dean Research and Development, St. Peter's Institute of Higher Education and Research, Chennai, in the first session, and he'll be inaugurating this session, and he'll be giving the keynote ISPA as well as the topic related condensed matter physics. And second session will be hosted by Dr. J. Salvan, Assistant Professor, Department of Nuclear Physics, University of Madras, Chennai. And tomorrow we are having 2 more persons. Dr. M. Arivanandan, Professor, Center for Nanoscience and Technology, Anna University, Chennai, will host the first session. And the second session will be hosted by Professor R. Jayvel, Director, Center of Nanoscience and Technology, Anna University, Chennai. So with these 4 people, just we are going to run this show. And I have been assigned the job of welcoming the people who have gathered here for this program. Of course, nearly 620 members have registered, and now the 60 to 20 members are joining with us. We are proud to say this much amount of participants have responded. Thanks for all the participants who have responded our invitation. And here we will switch over to the job of introducing Dr. S. Gunasekaran. Of course, there is no need for the people of spectrophysics to have an intro about Gunasekaran sir, because he is a well-known person. Anyhow, I have been assigned the job of introducing him because we feel proud to introduce him. Sir, we welcome all first, and especially our Dr. S. Gunasekaran sir. Welcome you, sir.
Thank you.
Dr. S. Gunasekaran is a Dean and Research and Development of St. Peter's Institute of Higher Education and Research, Avadi, Chennai. He has begun his teaching career at the Pachepos College, Chennai in 1978. And he was a person with a craze process. For your information, he was the external examiner for me. Of course, I am in the verge of retirement, but for my MSc examination, he was my external examiner. That was senior who is. We feel proud to have you as a part of our Jamal College Department of Physics activities, sir. And uh, actually, he is having his lab in research and development lab in support of management of St. Peter's Institute of Higher Education and Research. And he has established a sophisticated analytical instrumentation facility, Cipher, housed with advanced spectrophotometers. And his area of research are material science, medical physics, environmental science, and molecular dynamics. And of course, Dr. Gunasekaran is the father of the term spectrophysics. He has coined the word spectrophysics. Till date, Dr. Gunasekaran has successfully guided 75 candidates who have obtained their PhD in material science, medical physics, environmental science, and molecular dynamics. And he has published 400 papers in reputed journals with the H index of 32 and I-10 index of 121 with 4,605 citations. More than 4,600 means unimaginable it is. And he has filed 3 patents so far. He has been awarded with so many awards, and he is a part of the School Education Board of the Government of Tamil Nadu by serving the member of the Syllabus Revision Committee and chairperson of Book Writing Committee. He authored 14 books for higher secondary physics, secondary science, and environmental education in both Tamil and English medium. Dr. Gunasekaran had the honor of being selected for the post of Registrar, Periyar University, Salem, and this administrative post he served with verve and vigor for the full term of 3 years from August 2008 to August 2011. And he has instituted 4 C.V. Raman awards, 2 each for students and faculty in order to kindle the research thirst. And generally, he is to organize National Science Day celebrations every year on 28th of February. He is a man with high potential and, of course, with so much keen interest on his field. And he is down-to-earth character. And whenever we approach, he used to readily accept our invitation. And first of all, we thank Dr. Gunasekaran sir for accepting our invitation and made all the groundwork, because his name only spell, it's actually it was in the memory of each and everyone who has registered. Gunasekaran, under Gunasekaran sir's ages, we are doing this, and we pray God for him to have a very good health and a safe journey here. Even hereafter, just he has to guide so many people like us. Sir, we thank you once again, sir, for being a part of our MOU as well as our research activities in this regard. On the behalf of Department of Physics and Management of Jamal Mohamed College and Administration Group of Jamal Mohamed College, we thank you, and once again we welcome you, sir. So we can start it now.
Okay. Thank you, sir.
But now that the thing is, it has been transferred to Dr. S. Gunasekaran, who will deliver the keynote address as well as the inaugural address also. Thank you, sir. Welcome once again. Thank you.
Thank you, Professor. Thank you. Thank you. Our most respected head of the Department of Physics of the great institute, Jamal Mohamed College, and my good friend, Professor Dr. Jamal Mohamed Jafar. Our respected Professor Dr. A. Ishaq Ahmed, Department Coordinator of DBT Star College Scheme. My good friend and my beloved student, Professor Dr. Raja Mohammed, Coordinator of the Internal Quality Assurance Cell of this institute. Our distinguished speakers, eminent scientists in the field of nano science and technology, Professor from Anna University, Professor R. Jayavel sir, Dr. M. Arivanandam, Dr. J. Sendil Salvan, learned members of the Department of Physics of JMC, Jamal Mohamed College, and professors from various departments, participants, delegates from different institutions, both in Tamil Nadu and other sectors, young budding scientists, young philosophers, ladies and gentlemen. Vanakkam, Vantanam, Namaste, Namaskar, Suswagatam, and good morning to one another. In fact, as pointed out by our beloved HOD, Professor Jamal Mohamed Jafar, my first visit to the Department of Physics of JMC, so in the year 1992, as an examiner to conduct the MSc Physics practical examinations. In fact, my association with this department, because I visited so many occasions to inaugurate the conference, to deliver talk, other activities. Nearly, my association with the department is nearly 3 decades. This is my home institution. Like, I feel proud to have MOU with this esteemed institute, with our Indian Spectrophysics Association. In fact, there are 3 sentences, 3 good sayings about team spirit. I had occasions to observe the activities of the Department of Physics of JMC more often during the organization of national conferences, international conferences, workshops, FDP programs, or department level events. And very good team spirit within the department. Under the able leadership of the principals, vice principals, with the able guidance of the HOD, in particular the HOD of the present Dr. Jamal Mohamed Jafar. So, coming together is a beginning. Keeping together is progress. And working together is a success. So, to get the team spirit to organize an event, maybe an international event or state level event or national event. So team spirit is important. Team means together everybody achieves more. That's all. This is expansion for team. That's my opinion. Coming together is beginning, keeping together is progress, working together is success. So to succeed in an endeavor like this, organization of the faculty development program, team spirit is very, very important thing. And preparation is a necessary edge to succeed in an endeavor. Preparation is very, very important thing. Just during the introductory address given by our HOD, Professor Jamal Mohamed Jafar, I think in collaboration with the Indian Spectrophysics Association and IQAC of this institute, we are doing all kinds of activities to make this event a great and grand success today. So for which preparation is necessary edge to succeed in an endeavor. As per my knowledge is concerned, preparation is not an English word. Not English word. Is the preparation English word? My opinion, preparation may not be an English word. Preparation is a word of human thought. A word of human thought. That is a preparation is equal to planning. Planning plus principle. Principle plus practice. Practice and patience. So these are the 4 words we can give expansion for preparation. Actually, we have studied in biology. Up to 10th standard, I think we have studied botany also. There is no doubt in it. There is one concept in biology. For some species, many flowers combine together to give you a single fruit. Many flowers combine together to give you a single fruit. For example, Lancian tree, banyan tree, jackfruit tree. These are a very good example for this biological science. That is, many flowers combine together to give you a single fruit. ஏன்னா ஒரு பூக்கு தான் ஒரு பழன்றது கான்செப்ட், வெல் நோன் ஃபேக்டர். For some species, many flowers combine together to give a single fruit. அதுக்குதான் வந்து லான்சியன் ட்ரீ, பேனியன் ட்ரீ, இன் பர்டிகுலர் ஜாக் ஃப்ரூட் ட்ரீ, பலாப்பழம். ஒரு பலாப்பழன்றது சிங்கிள் பூ, சிங்கிள் பழம் சொல்றோம். ஆனா உள்ள இருக்கிற ஒவ்வொரு பலாச்சுளையும் ஒரு பூ. திஸ் சயின்ஸ். Many flowers combine together to give a single fruit. But here, Professor Jamal Mohamed Jafar, he has combined 4 flowers. That is, planning is one flower, then principle, then practice, then passions. So these are the 4 flowers. He is able to combine all these 4 flowers to give you a single fruit. The single fruit is today's FDP program on condensed matter physics. The fruit is very, very sweet today and having a sweet aroma also. Sweet aroma also. Therefore, on behalf of the Indian Spectrophysics Association, on my own self, I should congratulate the whole team of workers of this FDP program. In particular, the HOD Jamal Mohamed Jafar and coordinator of DBT Star College scheme, Dr. A. Isaac Ahmed, my beloved student, Dr. Raja Mohamed, and other faculty members to make this FDP program a great and grand success today. In fact, organizers have chosen a suitable topic as per guidelines of the DBT, Department of Biotechnology. They are given the topic, that is condensed matter physics. Condensed matter physics is more suitable topic for FDP, and which is more relevant to the current scenario, because all the speakers are going to deliver their talk in their areas. They come under condensed matter physics and materials physics. Material physics. Condensed matter physics and material physics have played a key role in technological advances in the modern era of science and technology. It plays a main role. That's why, and they have planned to organize this 2-day FDP program on condensed matter physics as per guidelines of the Department of Biotechnology. That is the Star College scheme. Impact. What is condensed matter physics? Because we are studying in our PG program. Condensed matter physics is the field of physics that deals with the macroscopic and microscopic physical properties of matter. But you must know the difference between macroscopic and microscopic levels, especially the solid and liquid phases, because we have to give more concentration on the materials which are available in solid and liquid phases, which arise from electromagnetic radiations of forces between the atoms of the molecules present in the materials, either solid phase or liquid phase. The key difference between macroscopic and microscopic properties is that macroscopic properties are the properties of matter in bulk, the whole bulk, whereas The microscopic properties are the properties of the constituents of the matter in bulk. This is the main difference between the microscopic level and macroscopic level. The macroscopic level includes anything seen with the naked eye, because you are all aware of that. Whereas the microscopic level includes atoms and molecules, things not seen with the naked eye. You could not see the atoms and the molecules. However, we can make investigation on atomic structure and molecular structure using highly sophisticated instrumentation methods. As you know, it's all basic things. These are all the units of measurement for macroscopic: centimeter, meter, kilometer, mega, and etc. etc. Very good example: volume, pressure, temperature, and pressure. And microscopic, what are the units measurements? Millimeter, micrometer, nanometer, picometer. The example is chemical bonding, intermolecular forces, intramolecular forces, and atomicity, number of atoms present in the molecular structure. The field of condensed matter physics overlaps with the material science, chemistry, engineering, and nanotechnology. Because condensed matter physics is not a single subject, which consists of a number of major areas like material science, chemistry, general chemistry, or chemical physics, or physical chemistry, engineering, and nanotechnology, and relates closely to atomic physics and biophysics. I think we could not consider a single major area. These are all some of the major areas that cover the condensed matter physics. There are two major research areas in condensed matter physics. You must know, because there are two major areas. That is called the soft condensed matter physics and hard condensed matter physics. Soft condensed matter physics and hard condensed matter physics. What is soft condensed matter physics? The constituents particles which are present in the bulk material, where the quantum chemical effects in their interactions can be neglected, are said to be subject of soft condensed matter physics, because the interaction is neglected here. Quantum chemical effects in their interaction neglected. If we consider the interaction, that is called hard condensed matter physics. That is the main difference between soft and hard condensed matter physics. Soft condensed matter physics are, you take statistical physics, numerical simulations, study of transport phenomena, thermodynamical measurements, optical scattering, neutron scattering, including X-ray scattering. So these are all some of the major research areas under soft condensed matter physics. What about areas of hard condensed matter physics? High temperature superconductivity, strong correlations, topological phases of quantum matter, quantum magnetism, phase Einstein concentrates, nanostructures, nanomaterials, the nanoscale, quantum computing, quantum chemical calculations, synthesis of new materials. So these are all some of the major areas under hard condensed matter physics, which covers many areas. My dear friends, the university systems, the university and the college sector, as well as research and development sector, are the major contributors to condensed matter physics. For any research area, extensive research is being carried out by the eminent people who are serving in the R&D laboratories as well as the higher education institutions. 1/3 of American physicists self-identify as condensed matter physicists. This is the data available in the literature. 1/3 of American physicists self-identify as condensed matter physicists. The division of condensed matter physics is the largest division at the American Physical Society. This is the weightage of the field condensed matter physics. In the last 20 years, more than 25 Nobel Prizes were awarded to condensed matter physicists. Just during the last 2 decades, more than 25 people were awarded Nobel Prize for condensed matter physics. You know, the father of the physics here. Who is the father of condensed matter physics? Who is the father of solid state physics, material science? As you know, there is one eminent scientist who invented 3 major discoveries in the year 1905. That is, in 1 year, a single man discovered 3 major discoveries: Brownian moment, photoelectric effect, and theory of relativity. So these are all the 3 major discoveries made by a single man, the great Albert Einstein. He is the father of solid state physics. And out of these 3 major discoveries, he was awarded the Nobel Prize for photoelectric effect. So to commemorate the completion of 100 years on these 3 major discoveries, 1905 plus 100 is equal to 2005. The world has celebrated International Year of Physics in the year 2005. This is the weightage you are giving to, honor you are giving to our great scientist Albert Einstein, the father of solid state physics. His 1905 article on photoelectric effect and photoluminescence opened the fields of photoemission spectroscopy and photoluminescence spectroscopy. So, all major 3 inventions, out of which photoelectric effect. His 1907 article on specific heat of solids introduces the effect of lattice vibrations on the thermodynamical properties of crystals, in particular the specific heat. As I mentioned at the beginning, Einstein is usually revealed as the father of special and general theory of relativity. He is also father of solid state physics, or even his broadened version known as condensed matter physics, including liquids. Yeah. During the correct who is the father of condensed matter physics? Literature data illa. He is the father of relativity, general and special theory of relativity. He is the father of solid state physics, or even his broadened version known as condensed matter physics, including liquids. I think this is a time for us to remember the human services rendered by our great scientist Albert Einstein. So what is the key role of condensed matter physics and material physics? Because we can't separate both condensed matter physics and material physics. Both are combined together. Because the invited speakers who are going to deliver their talk, they are going to emphasize not only condensed matter physics, also material physics. Condensed matter physics and material physics have played a key role in technological advances that has changed our lives in the last 5 decades. 5 decades. Because we are living in the world of science and technology. We are living in the world of modern materials. because of the invention made by our eminent scientists in this area. Driven by discoveries in condensed matter physics and material physics, have raised to several applications. What are the several applications? Such as development of semiconductors. Development of semiconductors. Dear friends, you must know the decade, that is one decade, 1920 to 1930, could be called as golden decade for physics. Golden decade for physics, especially for the Indian scientists. Indian scientists. You must know as a physicist. In the year 1920, Saga ionization formula. In the year 1924, Bose statistics. In the year 1928, the celebrated Raman effect. In the year around 1930-31, that is a Chandrasekhar limit. So these are all the four major discoveries made by our Indian scientists between 1920 and 1930. That's why 1920 and 1930 could be called as golden decade for physics for Indian scientists. Moreover, special mention may be made that in this decade only, for condensed matter physics and then material physics, the main backbone is the quantum mechanics. The new concept of quantum mechanics was introduced in this decade only. The new concept of quantum mechanics was introduced in this decade only. Without quantum mechanics, we can't have semiconductor physics. Without quantum mechanics, we can't have solid state devices. You are studying electronics, you are studying microprocessor, you are studying embedded system, PICs, IC chips, all because of the invention in the area of semiconductor physics. Without quantum mechanics, there is no semiconductor physics. You are using large computers, supercomputers, nanocomputers. Everything is using the odd circuitry. All our circuitry is made up of solid state devices. That is a basic building blocks. So the concept of quantum mechanics was introduced in the decade 1920 to 1930. Without quantum mechanics, we can't have semiconductor physics. That is solid state devices, embedded systems, microprocessor, microcomputers, microcontrollers, etc., etc. So this development. So basic thing is physics. That is quantum mechanics. Driven by discoveries in condensed matter physics and molecular physics, have raised to several applications such as development of semiconductors, the laser technology, integrated circuits, MRI, low loss optical fibers, the optical fiber communication, LEDs. Nowadays we are using OLED, magnetic recording disc, high performance composite materials, nanotechnology, etc., etc. We can count the number of areas, advantages, applications. Friends, condensed matter physics and material physics have played all these technological advances in modern era of science. And now we are living in the world of materials of modern world. Everything is based on these two subjects, condensed matter physics and material physics. Materials, everything is material. We are living in the world of materials of modern world. Materials. Dear friends, materials, new materials, advanced materials, biomaterials, biological materials, pharmaceutical materials, diamond materials, diamond-based materials, electronic materials, ferroelectric materials, fluorescence materials, functional materials, luminescence materials, magnetic materials, superconducting materials, materials for defense applications, materials for solar energy and energy storage devices, nonlinear optical crystals, photonic materials, smart materials, and nano materials, etc., etc., etc. Everything is based on all advances. The field of science and technology, everything purely depend upon the material synthesis, material characterization. Synthesis of materials and the characterization of materials, very important. My dear friends, after synthesizing the materials, one should be aware of sizes from macro to molecular level in nanometer. You must know, because we are the sizes vary from macro to molecular level. You take the bulk material I mentioned at the beginning, macroscopic level. The size is for bulk material more than 10 power 4 nanometer. More than 10 power 4 nanometer. The size in between 10 power 3 to 10 power 4 MEMS device on a silicon chip, and including living cells in our body. Sorry, for micro. For microscopic level, the size ranging from 10 power 3 to 10 power 4. Examples, MEMS device on a silicon chip, living cells in our body. What about nanoscale? 1 to 100 proteins, DNA, nanoparticles. The size varying from 0.5 to 1 nanometer. 0.5 to 1 nanometer. Small molecules, that is a molecular level. Molecular level. The size varies from 0.1 to 0.5 nanometer. Chemical bond, that is atomic level. You see, micro level, macro level, nano level, molecular level, atomic level. When you are going for characteristics of materials, you have to define macro level or micro level or nano level or molecular level or atomic level. For each and everything, we are having highly sophisticated instrumentation techniques for material characterization. How to understand about nanoscale parameter? Just a simple way. Day-to-day life. For comparison, you take the CC bond, C single character bond, CC bond, single bond, C carbon, single bond carbon. In an organic compound, for example, 12 to 50 nanometer normally. DNA double helix has a diameter around 2 nanometer. To be precise, the comparative size of nanometer to meter, because we are dealing with the nanoscale, nanometers, nanoparticles. What is the ratio between nanometer and meter? And which is equal to size of the marble stone which is available on the earth surface divided by size of the earth. That's all. Just imagine. So, to be precise, the composite size of nanometer to meter is equal to size of the marble stone to size of the earth. Width of human hair, 100,000 nanometer. Stratum corneum. This is the outermost layer of our skin in our body, which is found to be around 50,000 nanometer. In this way, we can understand about the nanoscale parameter. So these will explain and make one to understand about sizes from macro to molecular level. These are basic ideas. Dear friends, hence, emphasis should be given to give more importance on these thrust areas that is compressed or condensed matter physics and material physics. There's a material for model word. Synthesize, characterization. Because we are doing only synthesis of the material, then characterization. Maybe that kind of work is incomplete. Maybe this is a kind of work for our PhD work, PhD program or MPhil program. There is no doubt in it. But that will be incomplete work. So synthesize, characterization, and that should be ended with application. That is real research, research excellence. Synthesis of material, either molecular level or atomic level, or micro level or micro level or macro level or nano level, use the suitable techniques for material characterization and see its applications. So your research work should be ended with the application. So synthesize, characterization, and application. That is called the real research. That is research excellence. Dear friends, there is one cartoon, English cartoon. Very interesting cartoon. I have forest, no trees. I have rivers, but no water. I have cities, but no buildings. I have roads, but no payment. Guess who am I? So this is a cartoon. The question raised in the cartoon. I am none other than world map. Rivers, forests are there. So trees are not found. Rivers are there. They are mentioned. Water is not found. Cities are there. No buildings at all. Roads are there. They are not designed the pavement. Everything. So this is the world map. Why I'm recalling this cartoon, my dear friends? Because synthesis of material, characterization. With synthesis characterization, you are doing a lot of technical data in the published papers. Papers are published in Scopus index sources. Papers are published in Web of Science source data sources with high impact factor. Because your work is good work. You are publishing in peer-reviewed journals. There is no doubt in it. But work will be incomplete. Technical data is there. How the technical data should be useful to the society, that is real application. Therefore, your research article should be ended with application. That is real research, research excellence. Very, very important. That's why Indian Spectrophysics Association has coined very good one annotation. Concept development for inspiring innovations to bind science and society. Concept development for inspiring to bind science and society. The quality, quantity, and utility. That is called real excellence and real research. Outcome of your research, either in the form of MPhil dissertation, or in the form of PhD thesis, or in the form of paper publication, should be useful to the society. That is real research, research excellence. Then only we can aim for filing the patent, award of patent, approval of patent. That is very, very important thing. My dear friends, having all these points in your mind, showcase your brain management, showcase your time management, showcase your human resource management to provide quality culture in your education institution in terms of paper publication. Paper publication should be ended with the applications of your theme chosen. That is very important thing. Without application, synthesize, characterization. Don't limit with characterization alone. Should be ended with application. Very, very important thing. Then only citations of your paper will be more and more day by day. H&X of the individual author will be increasing gradually. H&S of your institution will be increasing gradually. In turn, Exchange suffer into our India will be approaching towards the rank number 1 America. That is important thing. At the beginning, we'll address young philosophers. You are all young philosophers. Master of philosophy, doctor of philosophy. You must know what is the actual meaning for philosophy. MA philosophy is the one program in humanities. That is different. MA philosophy. In Tamil, Tattvam. That is different. What is the actual meaning for philosophy in Master of Philosophy? Philosophy in Doctor of Philosophy, PhD and MPhil. I think more than 40% of the words which is being used in English literature were taken from other languages in the world. There is a research. More than 40%. There are 2 words in Latin language. One word is plus, another word is Sophia. The meaning for plus is knowledge. Meaning for Sophia is love. That's all. Tamil சொன்ன போனாக்கா knowledge என்றது அறிவு, love என்றது நேசிப்பது. That's all. அறிவை நேசிப்பதில் you are all masters. That is the master of philosophy. அறிவை நேசிப்பதில் you are all doctors. That is doctor of philosophy. அதான் இங்கிலீஷ்ல எடுக்கிறப்போ after taking these 2 words from Latin language, plus Sophia combined together, they gave a single word, philosophy. That's all. அறிவை நேசிப்பதில் you are all masters, master of philosophy. அறிவை நேசிப்பதில் you are doctors, doctor of philosophy. As philosophers in your chosen field, you may be aware of science and technology workforce in our higher education institutions in India or the global scenery. Important. You are all material physicists. All the researcher doing your research in condensed matter physics. You are doing research in the field of material physics, material science. So you may be aware of science and technology workforce in higher education institution. India's science and technology workforce is estimated to be just about 5 million. These are data, current data, 2022 data. அதாவது 1 மில்லியன் பீப்புளுக்கு 216.2 பேர் PhD பண்றாங்க. India's science and technology workforce is estimated to be just about 5 million people. That is 216.2 per 1 million. Compared to 1,200 for China and 4,300 for USA. You are making comparative study. In all areas, science, technology, medical, agri, then engineering, everything. According to latest statistics available with the Department of Science and Technology, just in the previous year, up to last December 2021, India ranked 3rd place in the number of total scientific publications, up from being ranked 6th in 2013, being ranked 12th place in 2006. 2006 12th place இருந்த இந்தியா 2013 6th place வந்தது. இப்போ 2021 we are in the 3rd place in terms of paper publication. Out of more than 190 countries in this globe, you are able to score 3rd place paper publication documents. That is citable documents. I mean, citable documents, not ordinary papers. Paper published in peer-reviewed journals with citation, citable documents. You are in the 3rd place. 1st place, China. Published 5,28,263 papers. 2nd place, USA. Published 4,22,808 papers. 3rd place, India. That is 1,35,788. Next, German. Okay. Last with Japan. We are in the 3rd place. My dear friends, if we take same country ranking in terms of H-index of the institution, H-index country. நான் சொன்னது வந்து பேப்பர் பப்ளிகேஷன்ல we are in the third place, global scenario. But the H-index of the country சொல்றப்போ first நிக்கிறது USA, அமெரிக்கா, having H-index 2577. India is in the 7th place, that is scored 691. அங்கேயும் பாருங்க பெட்டரா இருக்கு. 190 countries மேல இருக்கிற இந்த குளோப்ல பிளானட்ல we are scoring third place in terms of paper publication, and we are scoring 691. We are scoring 7th place in H-index country ranking. Here special mention may be made that, my dear friends, research papers published by world in condensed matter physics, as seen from Web of Science, is accounting for 35% share of the world output in physics. The data. But எல்லா ஃபீல்டும் சேர்ந்து science and technology, we are in the third place country. I mean India. H-index 7th place. அந்த பிசிக்ஸ்ல இருந்து பிசிக்ஸ் கான்ட்ரிபியூஷன் இருக்குங்க. தி டோட்டல் ஃபீல்டு அதுல வந்து பிசிக்ஸ் சப்ஜெக்ட் எடுத்து பிசிக்ஸ்ல இருந்து வாட் அபவுட் கண்டென்ஸ்ட் மேட்டர் பிசிக்ஸ், which includes material physics. Research paper published by world in condensed matter physics, as seen from Web of Science data source, is accounting for 35% share of the world output in physics. Similarly, research papers published by India in condensed matter physics, as seen from Web of Science, is accounting for 40% share of the country output in physics. Total percentage contribution out of physics complete total வந்து 40% contribution India இருக்குது condensed matter physics. Global scenario physics இருந்து 35% contribution by condensed matter physics. This is a pleasant data because we have chosen that is FD program on condensed matter physics. Very, very important thing. Dear friends, this was surprised by USA, China, UK, and Japan. Surprised. It is known that India's research productivity will be able on par with most G8 nations within 7 to 8 years. What is G8 nations? Leading advanced economics in the world group of 8 nations: Canada, France, Germany, Italy, Japan, Russia, UK, USA. Actually, according to current statistics available with the MHRD, Ministry of Human Resource Development, Tamil Nadu ranked number 1 in the enrollment of PhD scholars. I think most of the PhD scholars, they are choosing the field of material science, medical physics, biophysics, condensed matter, everything is materials. Tamil Nadu stands on the top with 25,820 PhD scholars, followed by Delhi with 19,119 and Uttar Pradesh with 13,300 PhD scholars. This is a pleasant observation. But Tamil Nadu stands first, number 1. At the same time, my humble request to the participants who have joined here, quantity is not important. Quality is very, very important thing. Quantity is not important. Quality is very, very important thing. To provide quality research work in your higher education institution, for which brain management is very, very important thing. Brain management in your research activities. You take Switzerland. There is one private company the name of Condensed. They produce costliest pen in the world. That is a golden pen with more than 5,000 pieces of diamond. Cost is 1.25 crore. 1.25 கோடி கொடுத்து பெண்ணை வாங்கினா போதுமா? ஒரு 10 ரூபாய்க்கு ஒரு ரீஃபில் வாங்கினாதானே பெண்ணை எழுதும். According to biology, the costliest living system on the earth surface is human being system. 6 அறிவு உள்ள ஒரு உயிரினம் வந்து நம் மனித இனம்தான். The costliest living system on this globe is the human being system. 6 அறிவு சொன்னா போதுமா? பயன்பாட்டிற்கு அறிவு வேண்டாமா? நம்ம பொறுத்த வரைக்கும் அறிவுன்றது ரிசர்ச் knowledge and research. My dear friends, to acquire knowledge, to acquire brain management, research activities, you have to showcase your brain management to provide brain management, time management, and to read many number of articles in your field. You take a honeybee, a single honeybee has to travel more than 10,000 flowers to collect 100 grams of honey. Nectar, not honey, nectar. அந்த honeybee nectar தான் குடிக்குது பூவுல இருந்து. அது டைஜஸ்ட் குடிச்ச ஹனியை நெக்டரை டைஜஸ்ட் பண்ணுது இல்லையா? அந்த டைஜஸ்ட் பண்ணப்பட்டதா நம்ம குடிக்கிறோம். that is honey. In order to collect 100 grams of honey, a honeybee has to travel more than 10,000 flowers, for which it has to travel 1.5 lakh kilometers fly. It has to fly more than 1.5 kilometers. To get 26.4 gram of gold, pure gold, from the ores, we need 1,000 kg weight of ores. Why I am telling all these things? Synthesis, characterization. We are going to project the applications also to provide research excellence in your area, condensed matter physics or material physics, and for which we have to read hundreds of articles. Then only we can provide quality research papers that will be published in database journals, peer-reviewed journals, highly reputed journals, which are indexed both Web of Science and Scopus. Very, very important. Reading habit is important. You take our beloved scientist, Dr. K.S. Krishnan, a grand scientist, beloved student of our father of Indian science, the great Sir C.V. Raman. Yes, mentioned in his article. My wholehearted involvement come only after 8 years, when I got opportunities to read copies of research articles of Sir C.V. Raman. This gave me a new feeling for science and the world of science. If you refer 6 volumes of publications published by Indian Association of Cultivation of Science. First volume optics, another volume optics of diamonds, then scattering of light, physics of crystals, acoustics, floral colors and visual perception. These are 6 volumes of publications by Sir C.V. Raman, published by Indian Association of Cultivation of Science, Calcutta. So இந்த 400 பேப்பரும் அவர் படிச்சு முடிக்கிறதுக்கு 8 வருஷம் ஆச்சு. 8 வருஷம் ஆன பிறகுதான் வந்து அவர் ரிசர்ச் பண்றதுக்கே ஒரு இன்ட்ரெஸ்டே வருதுன்றார் K.S. Krishnan, blood student of Sir C.V. Raman. This is research excellence. இதோ ஒரு பேப்பர் படிச்சு இதோ ஒரு சர்வே பண்ணா ஒரு மனித 3 வருஷம் தீஸ் படிக்கல. 3 வருஷம் படிங்க முடிங்க தீஸ் இல்லைன்னு சொல்ல. பட் should be research excellence. Very, very important thing. My dear friends, the junior researcher, for example, he is asking a senior researcher, because to provide quality research work, I am giving some clue. Or junior researcher asking a senior researcher how to provide quality research articles. for which the senior researchers gave a reply to that junior researcher. Thambi, to provide quality research work in your area chosen, so உனக்கு 4 மைகள் தேவைப்படும். அந்த பையன் என்ன பண்ணிட்டான்னா, பேப்பர் எழுதுறதுக்கு 4 மைனா ப்ளூ மை, கருப்பு மை, கிரீன் மை, ரெட் மையா நினைச்சிட்டான். என்னென்ன கலர் மை சொல்லுங்க சார் பையன். தம்பி, அந்த மை சொல்ல பொறுமை, தனிமை, திறமை, பேனாமை. பொறுமை, தனிமை, திறமை, பேனாமை. So இந்த 4 மை இருந்தால் we can give quality research papers, quality research work for your PhD program. That is without any plagiarism. That is important. தொடக்கூடாத மைகள் சொல்றாரு பாருங்க. கயமை, பொய்மை, மடமை, வேற்றுமை. That is a plagiarism. இப்போ 10% மேல ஃபிளாயர்ஸ் இருந்தால் வந்து பேப்பர் வில் பி ரிஜெக்டட். நீங்கள் பிஹெச்டி டிகிரி வாங்கின பிறகு ஆஃப்டர் 10 years பொறுத்து ஃபிளாகரிஸ் இருந்ததுன்னு சொன்னாங்கன்னா யுவர் டிகிரி வில் பி வித்ரான் பை யூஜிசி. தொற்று எழுதக்கூடிய மைகள் நன்மை தரக்கூடிய நேர்மை, திண்மை கொண்டிருக்கும் புதுமை, தூய்மை தரக்கூடிய செம்மை, வலிமை தரக்கூடிய உண்மை. இந்த நோக்கத்தில் ஆராய்ச்சியாளர்கள் தங்கள் கடமையாகவும் உரிமையாகவும் கொண்டு தமது இந்திய நாட்டிற்கு பெருமை சேர்க்க வேண்டும். This is the advice given by a senior researcher to junior researcher. Important thing. Therefore, my dear friends, having all these points in your mind, there is one book written by a retired professor of IIT Chennai, former professor of IIC Bangalore, by name R. Parthasarathi. The title of the book is Paths of Innovators. That is 2 volumes, volume 1, volume 2. It comprises a collection of scientists, their lives, their struggles, their achievements, and their laurels. In mathematical science, 62 innovators. Physical science, 73 innovators. Chemical science, 44 innovators. Life sciences, 36 innovators. And science and technology, engineering technology, 76 innovators. Total of 291 innovators. He has written the life history of 291 innovators in these 2 volumes of book. For each and every innovator, he has given 4 to 5 pages. That's all. ஒரு innovation, ஒரு innovator ஒரு நாள் படிங்க. Within 291 days, we can complete both the volumes. பொறுமையா படிங்க, ஒரு half an hour படிங்க போதும். படிச்சாதான் தெரியும் உங்களுக்கு. We can get self motivation towards to provide quality research work here. You have to create your own ecosystem for innovation. All these 291 innovators, they have created their own ecosystem for innovation. Again, I am telling, our Indian Spectrophysics Association have coined another 2 annotations regarding the quality research work. That is cognitive framework to edifice a sustainable research culture in higher education institution. The next one is cultivation of research excellence to enhance innovations and professional developments. So these are all the some annotations coined by ISPA. That's it. These are all annotations coined by ISPA to motivate the researchers and to create their own ecosystem for innovation. Therefore, my dear friends, participants, young budding scientists, young philosophers, professors, researchers, having all these points in your mind, you have to showcase your brain management once again. You have to showcase your time management. You have to showcase your human resource management to provide quality research work in your higher education institution. That is very, very important thing. மோரை கடந்தால்தான் வெண்ணெய் எடுக்க முடியும். மோரை கடந்து வெண்ணெய் எடுப்பதை போல் அறிவினை வளர்த்து ஆராய்ச்சியின் பலன் பெற வேண்டும். கண்களால் பட்டாம்பூச்சிகள் பறப்பதை பாருங்கள். காதுகளால் பறவைகள் பாடுவதை கேளுங்கள். மூக்கினால் மலர்களின் வாசத்தை நுகருங்கள். வாயினால் உண்மையின் மகத்துவத்தை பேசுங்கள். கைகளால் பயனுள்ள கவிதைகளை எழுதுங்கள். கால்களால் நடைப்பயிற்சி செய்யுங்கள். மூளையினால் பயனுள்ள ஆராய்ச்சியினை மேற்கொள்ளுங்கள். தன்னம்பிக்கையும் நேர்மையும் கொண்ட எந்த ஆணும் அழகன்தான். கனிவும் பணிவும் கொண்ட எந்த பெண்ணும் அழகுதான். Don't dream about your beauty. That will spoil your duty. Dream about your duty. It will make your life very beauty. Innovations come from creativity. Creativities come from beautiful minds. Therefore, நீங்கள் தவறி கிணற்றில் விழுந்து விட்டால் கவலைப்படாதீர்கள். வாய்ப்பை பயன்படுத்தி குளித்து விட்டு வாருங்கள். நீங்கள் எழுந்து நின்றால் அந்த இமயமலையும் உங்களுக்கு இடம் கொடுக்கும். நீங்கள் உறங்கி கிடந்தால் அந்த சிலந்தி வலையும் உங்களை சிறைப்பிடிக்கும். உலகை பாருங்கள், வியக்கலாம். உழைத்து பாருங்கள், ஜெயிக்கலாம். நினைத்து பாருங்கள், சிந்திக்கலாம். உங்களுக்கு நம்பிக்கை இல்லையா? அதோ பாருங்கள் நம் அப்துல் கலாம். Therefore, my dear friends, get ready, go ahead, kindly participate in your research activities, demonstrate your full skill to provide quality research work. Get awards and make it a record. Wish you all good success. Thank you very much.
Thank you, sir, for your nice presentation.
Thank you, sir.
Dear
Thank you.
participants, if you have any doubt or any clarification, you can ask our resource person.
Okay.
There is no question.
Okay.
We come to the end of the session. It's a time for formal vote of thanks. I invite Professor A. Mohamed Salim, of Associate Professor of Department, to propose the vote of thanks. Morning to all. So it is my pleasure to propose the vote of thanks. So first of all, I thank Almighty for abundant blessing on us. So next, I thank Secretary and Correspondent for acceptance of our request for MOE with the Indian Spectrophysics Association, Chennai, to exchange and enrich the knowledge among the faculties and the research scholars and the students. So next, I thank the Treasurer, Assistant Secretary, and the member in Management Committee for their kind support and constant encouragement to conduct the faculty development program. The next, I thank the principal to motivate the staff members and the students to organize and involve such academic activities. And I thank the vice principal, additional vice principal, and the directors of the hostel administration for the kind support. I thank Dr. S. Gunasagaran, Tamil Nadu Scientist Awardee, Dean Research and Development, St. Peter's Institute of Higher Education and Research, Chennai, who delivered the inaugural and keynote address in this faculty development program on condensed matter physics and the DBT Star College scheme. He highlighted the importance of the condensed matter physics. So he is not a stranger of our college. He is part and parcel of our department. So then and there, our staff member will interact regarding the research and other academic activity. So he helped us a lot. So in that way, so I have to thank once again. So thank you, sir. I thank our head of the department, Dr. M. Mohamed Jafar, who delivered welcome address and initiated the MOU with the Indian Spectrophysics Association and to organize the faculty development program for the benefit of the staff members. I thank the faculty member of our department and the faculty members from various departments and from other colleges for their participation and kind cooperation to conduct this FDP successfully. I thank to the department DBT coordinator, Dr. A. Isaac Ahmad, and the staff in charge, Dr. S. Sheikh Daw. The DBT program helped to conduct this FDP. So once again, I thank you all. Thank you very much.
Thank you, sir. Thank you very much. Thank you. Thank you. Thank you.
Sir,
Thank
it is
you,
special
Professor.
thanks from Department of Physics. Thank you, sir. Thanks
Thank you,
once
Professor.
again.
Thank
We
you,
have started.
thank you, Professor.
Good
Thank you,
start
thank
is half done. So we have started it and everything will go smooth in accordance with our plan, sir. Thank you. Of course,
Thank
the next session will start within 10 minutes. Before that, just we want to spare some information regarding the facilities available in the Jamal Mohamed College Department of Physics and what are the programs that we are undergoing for the benefit of the students as well as the staff community. We want to share some information regarding this. Actually, we are running the program DBT Star College scheme program we are running. This is the second year for ourselves. Of course, this information is for the participants. Of course, we can have any interaction with ourselves. Always you are welcome because we are doing our best regarding the DBT scheme. Of course, we have undergone nearly 4 to 5 memorandum of understanding with the various institutions. Of course, the primary thing is with ISPA, the Indian Spectrophysics Association, under the aegis of Dr. Gunasekharan sir, senior brother. Actually, he is rendering all the help for us, and we are forwarding the students, and of course, we are having the interaction, and we are having the staff and student exchange program for this. And of course, we'll be highly benefited out of the encouragement given by Dr. S. Gunasekharan sir. In all our endeavors, he is the prime source and he is the confident giver. Of course, he is the man behind that total screen he is behind, and the success is only because of him after the help of God. He is doing all the best for us to go for the program in a grand success, of course. And in due course of time, of course, we'll be having several student programs. This program is meant for the staff alone. It is faculty development program, so it is meant for the staff members. And in due course of time, we will have our programs for students also. And of course, any help from our side, and of course from ISPA side, we can in the field of not only in spectrophysics alone, of course, in electronics or microprocessor, all the things. Of course, he is a man who is having basic interest in microprocessor and electronics. Of course, I met him only as an electronics examiner because I had a very good experience with him in the battle examiner as a co-examiner. All the experiences I had with him. So, apart from spectrophysics, he has very good experience in the electronics as well as microprocessor concepts, of course. So whatever the help you need, please don't feel hesitated to contact us. We will have a rapport, and the rapport will be extended towards Gunasekharan sir, and we can have all sort of help expected from your side. So don't have any hesitation. Of course, don't think that it is only a 2-day program, and of course the relationship will be cut out after 2 days. No, it is going to be a good start. Of course, we can have an intro, so that all the people we can have the interaction with Gunasekharan sir through us, and of course we can have a very good forwarding action in this particular field. So sir, shall I take this as a thing, sir? Shall I pass information to the participants like this?
Oh, okay, sir. Definitely, sir. Definitely, with pleasure. Pleasure, sir.
Thank you, sir. Thank you, sir. When the man is like this,
yeah.
When he is like this, we can be benefited. Don't worry, just all the participants, whatever sort of help just you want to have, just we can have it through the Dr. Gunasekharan sir, of course.
Yes, sir.
And of course, MOU, first MOU with this, and second MOU we are having. Yes, we are having second MOU is with ISPA. Yeah. Yes, yes, Decibel Institute. Of course, we are having an institute, Decibel Institute in our Tiruchirappalli itself. And of course, we are having the MOU with them so that we can forward our students. And of course, they are giving training for cell phone servicing and all. Of course, it is a job-oriented package. And of course, we are having the staff exchange program between ourselves and the expert exchange from their side. Of course, we are sending the boys to that particular lab, and they are getting every help from them how the cell phones can be serviced. Of course, after completing the BSc or MSc, they can start their own firm so that they can have self-employment. Of course, so in that regard, just we have an interaction with Decibel Institute, and of course, thanks to the people concerned. And the third MOU is with Sigru Collab in Bangalore. Of course, we are having our astronomy club in our department, PG and research department. We are having an astronomy club, and this is Vainu Babu Astronomy Club we are having in our department, and we are having a telescope which is having more power than our resolving power as well as magnification power than the telescope in our planetarium itself. Of course, we are having very good link with the people in planetarium, the director Ahilan sir, and of course we are having Jayapal sir and Bala sir, Trichy Astro Club, and Manohar TNSF Manohar sir, Shanti ma'am from TNSF. So all the people, they are helping us, and in this regard we are having our own link with all these people. The Sigru Kolara, it is having the link with ISRO as well as NASA, and of course we are planning of starting a center for astronomy club. Center for Astronomy in Tiruchirappalli we are going to start, and of course we'll be getting the data from ISRO as well as NASA directly, and we will be having our students. Of course, already 5 students are undergoing training for analysis of the data given by the NASA as well as ISRO. After identifying all these things and are having a perfect analysis of this, the students will be capable of having an exposure towards the identification of small planets, that is Kurungolgal identification, that is asteroids and all these things. They are having a plan of doing this. So meteors they are going to identify, and all these things are started under the aegis of this Sigru Collab, and of course the person concerned, Surendra, Mr. Surendran is our proud alumnus. Of course, he is working there, and Ram also is there. Just we are having a very good link. So we are having this type of work undergoing here. So we are having the MOU with them, and we are having the plan of starting a center for astronomy in Tiruchirappalli, which is going to be a link between NASA, ISRO, and Jamal Mohamed College. We can have a triangular relationship. So we can have the participants, you can have any help from us soon. Okay, and the next one is Balaji Institute in Bangalore, of course, Coimbatore, and of course we are having link with them, and they are having software packages. That is for editing software packages. They are giving the training for our students. Of course, after finishing MSc Physics, the students can directly go to the editing field, of course, which is a money fetching field. It is the TV programs or else cine programs. They are having software editing. They are having packages. So that packages training is given by those people for our students, and of course, the software training also given by our staff members. So we are having a link with Balaji Institute, and of course we are having Viscom in our college. So the people who are concerned with that, they are also having the link with us. So in this regard, we have an exposure. It is also a self employment package, or else the job can be easily obtained by the people who got the training in this, of course. And we are having several facilities in our department. Next one is entity link. Actually, after we are having our proud alumnus, actually a person, Subaya sir, Mr. Subaya, who as direct radiation safety officer. He worked as a radiation safety officer, and after his retirement, he is helping us. Actually, we are running non-destructive testing programs in our department. Hands-on training program also we are running with the help of the NDT lab facilities given by Subaya sir. So we are doing our best, and of course the people who are undergoing the training there, they can complete the level 1, level 2 examination, and they can easily get the job in Singapore, Malaysia, and all these things. So our students are capable of getting easy jobs in NDT. So with the help of our Mr. Subaya sir, our senior, who has completed his PUC, BSc, MSc in Jamal Mohamed College in 1963. When I was born, actually, 1963. That much senior he is, but he is so young in his activities. So he is helping a lot, and we are doing our best in this regard. And one more thing, that is our ham radio, amateur radio club we are having in our department, and we are having our resource persons in Bangalore. Of course, we are having our own center here. We are planning of starting a center for ham radio in Tiruchirappalli division also. And of course, the data will be given from so many people. And of course, the specialty is the students who are going to participate here, they can construct a receiver and they can receive international calls. And next stages, they have to undergo an examination, and that they have to get a training, and they have to clear an examination. If they clear the examination, then only they are eligible for constructing the transmitter circuit. When you are clearing the examination, your name will be put up in the register ledger of Rashtrapati Bhavan in Delhi, and your name will be put up there, and you are the eligible person to operate the ham radio. So we have two resource persons in our college itself, of course, Dr. Aslam and Farooq, what's his name? English department. Parvez Sharif, Dr. Parvez Sharif we are having. Of course, these two people they are having a collaboration with us, and we are having the basis for this, and we are planning of starting a center and as Tiruchirappalli Center for us for ham radio. And the persons will be having interaction, and the students will be registering all the international calls, and they'll be registering the informations. Of course, we are going to start a fresh one. So, where? What program? Astrophysics, so we are having this much program in our department. Of course, the participants feel free to have any sort of help from us, and with the help of the eligible persons, and of course the highly talented people we are having in our hands, like Gunasekharan sir, we are having so many people. Of course, we don't think that we are two-handed, we are multi-handed, and each and every hand will be from the various sectors of our association. So we have to thank the people who are always offering their help to us. So I take this opportunity to thank everyone who is helping ourselves for the excellence of this much level. So once again, I thank everyone who is along with us, and we pray for everyone's good health, and we pray God Almighty to shower the blessing on each and every people who are helping us. So the participants, feel free, don't hesitate, just have an interaction with us for every help you need. Okay, so this session is over with the guidelines from our Gunasekharan sir and the blessings from Almighty. I thank once again everyone who is helping in this particular regard. Thank you once again, and we'll move to the next session. Next session by Dr. J. Salvan from Madras University. He is, of course, he is going to join us soon. He is in the department, of course. He will be joining soon, and we can have a program. Okay. Thank you once again, sir. Thank you.
Thank you, Professor. Thank you. All the best.
Sendil Salvan sir, the link பாருங்க.
Sir, good morning, sir. Hello, sir. Hello.
Hello, Salvan. Hello.
Hello, sir. Good morning, sir.
Good morning.
Sir, this is Dinagram from GRT Institute of Engineering Technology, Tirutani, sir.
Okay.
Sir, thanks for conducting this wonderful webinar and sending in invite for me. Sir, can I speak to our last session chief guest, Dr. S.G. Gunasekharan, sir?
Gunasekharan, sir.
Okay.
Sir, Gunasekharan link, sir. Yes, you can talk.
Okay.
You can talk.
Sir.
Okay. Good morning.
Sir, vanakkam, sir.
Vanakkam.
Sir, I am very proud to see you very long time, sir. I am former student of Pachabas College
Is it?
in the year of
Nice.
2005 to 7, sir.
Oh, very good, very
So
good.
you are handled 8086 subject, sir.
Microprocessor. Yeah.
Yeah, yes, sir, microprocessor.
Nice.
So right now I am working in GRT Institute of Engineering Technology, Tiruchirappalli, sir.
Okay, nice.
My MSc project is crystal growth,
Okay.
and MPhil DFT studies, theoretical studies.
Okay.
Still, I am not going to complete my PhD work, sir.
Okay.
Due to some family situation and financial situations, I can't do my PhD.
Okay.
But I tried my PhD in Anna University and also Sankara University, sir.
Okay.
அவங்க என்ன சொல்றாங்க அப்படின்னா, உங்க எம்எஸ்சி ஒரு டாபிக், எம்ஃபில் ஒரு டாபிக் இருக்கு. நான் இப்ப நானோ ஃபீல்டுல பிஹெச்டி பண்ணலான்னு ஐடியால நான் அண்ணா யூனிவர்சிட்டி அப்ளை பண்ணி என்ட்ரன்ஸ் கிளியர் பண்ணேன் சார்.
ஓகே.
பட் இந்த இன்டர்வியூல தே ரிஜெக்டட் மீ சார்.
நோ நீட், பிகாஸ் எம்ஃபில்ல நீ எடுத்த தீம், அதே தீம்ல யூ ஆர் சூசிங் எ ப்ராப்ளம் இன் ஃபார் யுவர் பிஹெச்டினா அந்த கோர்ஸ் ஒர்க் இருக்கு இல்லையா, கோர்ஸ் ஒர்க்.
Yes, sir.
That will be exempted. That's all. Coursework will be exempted.
Okay, sir.
However, the University Grant Commission has sent one circular to all higher education institutions to implement one special paper on research publication ethics, RPE. அது compulsory. They have made it compulsory. அது ஒரு பேப்பர் எழுதினா போதும். நீங்க சப்போஸ் அதே எம்ஃபில் டிசர்டேஷன் பண்ண அதே ஃபீல்டில் if you choose the problem for a PhD. Suppose otherwise you are choosing some other problem வச்சுங்க, other than your MPhil thesis வச்சுங்க, no problem. You have to appear for a course 3 course work along with the UGC ரெஃபர் பண்ண அந்த ரிசர்ச் பப்ளிகேஷன் பேப்பர் எழுதினா போதும். அதுக்காக வந்து எம்ஃபில்லும் பிஹெச்டியும் டிஃப்ரெண்ட் ஃபீல்டுன்னு அவசியமே இல்லை. சப்போஸ் ஒரே ஃபீல்டு ஆச்சுன்னா கோர்ஸ் ஒர்க் வில் பி எக்ஸம்டட் when you are doing PhD. 3 பேப்பர் எழுத தேவையில்லை, நேராக வந்து ரிசர்ச் பப்ளிகேஷன் எத்திக்ஸ் பேப்பர் மட்டும் எழுதினா போதும் ஆஸ் பர் யூஜிசி கைட்லைன்ஸ். நீங்கள் வேற ஃபீல்டு சூஸ் பண்ணுறதா தே ஆர் கிவிங் பெர்மிஷன். கண்டிஷன் இஸ் யூ ஹேவ் டு கம்ப்ளீட் த கோர்ஸ் ஒர்க் டூ த ஃபர்ஸ்ட் இயர். தட்ஸ் சார். ரிஜெக்ட் பண்ணக்கூடாது, ரிஜெக்ட் பண்ணக்கூடாது. டோன்ட் வரி.
ஓகே சார். தேங்க் யூ சார். தேங்க் யூ so much.
All the best, Papa. Thank you. I'm proud because you are the alumni of our Pachapas College, you know.
Yeah, definitely, sir.
Excellent. Nice.
Thank you, sir.
Thank you.
Yes. அப்படியா?
அந்த phone
செந்தில் ஒரு நிமிஷம்.
சொல்லுங்க சார்.
யாருடைய phone cut பண்ணணும்?
சரிங்க சார்.
Yes. So this is the second session.
Screen sharing.
Yes. The second session. Jason Salvan, a best friend of mine. Of course, he was my co-worker. Actually, we have worked together in the laser material processing. I have completed my PhD in NIT in this same field where Jason Salvan has worked, and of course, he was actually the pioneer at that time for us. He was a forerunner for us in this particular field. Thank you, Sendil, for this, because you only just opened the eyes in this particular field. And Dr. J. Sendil Salvan is going to host a second session from 11. And the topic will be photon up conversion nanomaterials and their bio applications. He is going to deliver a talk on this. And of course, he is going to be introduced by the Dr. A. Mohamed Salim, and over to Mohamed Salim.
Thank you, sir.
Morning to all. Welcome to the second session. The topic of this session is the photon up conversion nanomaterial and their bio applications. So, which is going to deliver Dr. J. Sendil Salvan. He acquired a PhD in laser processing of materials from Anna University in the year 1999. Then he worked as a lecturer in SRM Valiammai Engineering College during 1999-2001. He was a research professor in Kwanju Institute of Science and Technology, Korea in the year 2002, and worked in laser chemical vapor deposition. After that, he pursued postdoctoral research through JSPS fellowship in Professor Toshiaki Sohara's laboratory at Osaka University, Japan, and also in Tohoku University, Japan by Nano fellowship in the field of optical waveguide for photonic applications during 2003-2007. Dr. J. Sendil Salvan is working as assistant professor in Department of Nuclear Physics of University of Madras from 2008 onwards. His research interests are in laser surface engineering, optical nanomaterial, and photovoltaics. He has publication in several international journals and conferences. He got research funding to about ₹1 crore through various funding agencies and guided many MSc, MPhil, and PhD students. So with this brief introduction, I invite to deliver this lecture session. I hand over the session to Dr. J. Sendil Salvan.
Okay. A very good morning to everyone. First of all, I thank Professor Gunasaran sir actually for inviting me to present. I should thank actually Professor Professor actually for inviting me to present this talk. I thank actually Professor Jafar sir and for inviting me to present this talk on online faculty development program on condensed matter physics. It's actually very good high privilege for me to present this talk. So first of all, actually, I should thank actually Professor Anbadagan sir because Professor Gunasaran actually asking me to through Professor Anbadagan sir for giving this lecture about this faculty development program. And as Professor Jafar pointed out that actually we worked in the initial time of laser materials processing. So it's very hard actually the topic. So this particular laser material processing is associated with metallurgical engineering and materials engineering, mechanical engineering. And I want to share actually some of these hard moments that we have faced like during our PhD program. And that time, we don't have much kind of a high power lasers. So we used to go to the Indore, actually Madhya Pradesh by train, right? And there is only one high power CO2 laser was there, and it was indigenously developed. And when we go there, actually sometimes these laser instruments is not working, and we have to wait quite for about 1 month. And during 1 month time, we will have to say go to the library and visit various centers in Rajaramana Center for Advanced Technology Indore. And after waiting for 1 month, and suddenly the CO2 laser starts working, and we used to process the samples in 1 week time, and then we characterize. And also nowadays we have so many good facilities for young researchers like CM, XRD, and during our time actually in 1994 to 1999, there are not much good facilities, and we have to wait for so excellent facilities available only in IIT, right? So for taking FESM or XRD, we will have to wait for about 6 months to 1 year. So that much of hardship actually we face. But however, say this laser material processing, put actually great interest on me to work in laser related work. And slowly I move on to say laser associated with the say nanomaterials. And one such actually some photonic materials, what we call as the conventional nanomaterials. And this has quite good applications in various fields. And here in this talk, I wanted to focus on bio applications of conventional nanomaterials. So first actually I give the principle of conventional luminescence, and then I will give an overview about various conventional nanomaterials. And more specifically, I would like to focus on the conventional nanomaterials, how it's useful for bioimaging of our cancer cells, and how it's useful for photodynamic therapy. So how these conventional nanomaterials can be used as a the nano container or nano vehicle for targeted drug delivery. And another one is neurophotonics, that is related to optogenetics. And apart from this biological application, then these conventional nanomaterials have been used for biosensing and food analysis, and as well. So there's quite a number of applications, say even in solar cells, fingerprinting, and national security applications, and so many things are involved in that. But specifically, I wanted to focus on bio applications of the conventional nanomaterials. Okay, so before I want to start actual lecture, then this is actually customary for me to give a small actually that couplet about say Tirukural. Say everyone of us know well that say it's a highly secular in nature. So almost all these couplets are there. So, and specifically related to our education is concerned, and our teachers, either the teachers or students, then we have to keep on enhance our say knowledge and skills and day by day. So every day is actually a learning process for the teachers. So every day is a learning process, right? So this is similar to that actually, according to the couplet of Tirukural, then Totani Thurum Manarkani Mandarku Kattani Thurum Arivu. So that more we learn, more we acquire the knowledge, and more actually we can deliver this knowledge to our students, then the students will flourish in their life. Okay, so and regarding this particular couplet, and just I searched how I can associate these Tirukural with say photonics like that. But however, I find something related to that. Say what is actually that so something Tirukural in Tirukural, how Tiruvalluvar outlined about the lamp or light, and he correlate actually that good habits of a good person, right? So Ella Vilakkum Vilakalla Sandrorku Oya Vilake Vilakku. So Sandror, so the noble person and highly privileged person, so always actually express their actually the frankness, right? So in truth, actually that truth never trumps actually that. So always actually that say vaimeye vellum அப்படிங்கிற நம்ம தமிழ் இருக்கிற மாதிரி. So எல்லா விளக்கும் விளக்கல்ல சான்றோர் பொய்யா விளக்கே விளக்கு. So he highlight actually the photons, the light in terms of the characteristics of the person. Okay, with this actually, and let us move on to that actual our topic. So this particular talk is related to that of luminescence. Just a moment, okay. And this Kumar. So how to move this one here? Move this. No. Okay, yeah. So right, okay, so yeah, I will cut. So this is actually kind of condition nanomaterials is nothing but actually kind of luminescence material. So we can say that actually luminescence in terms of actually then a Sanskrit word or Hindi word or now, okay, so the prakasham, that means actually light, that is illumination. So this is actually that how we flourish our thoughts and minds actually, right, in a positive way. And if we think actually every time, every moment, if we think every as a positive way, then we have the positive vibration. Then, so we have the say the feeling of goodness, just like a light illumination. That how it actually fills that entire the space and how it opens the say lightness in the the room. So like that, actually the luminescence is actually related to the phosphor, and this also related to the Greek word. This derived from the word Greek word. The phos means actually light, and for us means actually bear. So something that material that bearing the light emitting behavior. That is what we call the phosphor material. So upconduction material is the kind of say a phosphor material, or we can say it's a luminescent material, or we can say upconversion nanophosphor, like that. So how we feel actually the smile of the child, actually how this is actually what is the prakasham. So the innocent, the mind actually, right? So just like actually how the innocent child actually smile, and like that the material smile when it actually illuminate with certain light, and that emits light in some other wavelength. So in one wavelength it absorbs, in another wavelength it emits, and depending upon how actually the material absorbs the light in one wavelength and how it emits in another wavelength, and depending upon that we can categorize actually the material into either the down conversion material or the up conversion material here. Okay, so this is actually another kind of say the joyful moment when actually the people enjoy during the holy time. That is actually so the colorful the nature. So always actually luminescence is associated with the emission of the colorful the light, and so whenever the people work with a certain luminescent material, whenever they find that desired result, then they will actually say have a good joy in their mind, just like that holy people how they enjoy the holy. So luminescence is nothing but the emission of the colors like this. And so otherwise we can say that the luminescence is associated with the say the several kind of materials. So when you look at that actually the periodic table, then we have the so many varieties of the material, and this is the kind of actually the sapphire crackers, that is in Tamil we used to say the bushwanam, like that. So how it actually emits the colors, and the different bushwanam like that emits colors in different actually colors, that depends upon how different actually the salts of different salts are that. Say for example the strontium salt, red colorization is actually due to that, and barium, so the green colorization lithium nitrate, and associated with that the pink colorization sodium, yellow color, so copper, a blue color, like that. So many actually so materials are actually useful to give the color in in different wavelengths. Say, and this is actually the when I go into that before going into that upconversion nanomaterial, let us say have a look on say the first luminescent material. The first luminescent material that is actually scientifically say explained about the luminescent behavior is by using the Bologna stone. That is the first luminescent material that reported in 1603. Even before that, we have actually so many Navaratna Karkal, like that, Navaratna stones. So these Navaratna stones have a different property of the color emitting behavior. And even before 1603, when actually these are scientifically explored about the luminescent behavior, and we have actually in our country, we have the so many kind of the luminescent materials, and scientifically reported material. The first scientifically reported the phosphorescence material is say Bologna stone is nothing but the barium sulfate. That is a combination of actually the barium sulfide and the copper sulfide. So the complex of actually barium sulfide and the copper sulfide when it actually absorbs the light, and that gives actually persistence luminescence. So this is actually that of the first reported material about the first luminescent material in that case. And this is about actual natural luminescence. Not only the various minerals and crystals emits light, but as well some kind of actual jellyfish or even say the mini puchigal like that will give certain kind of the autoluminescence, that is the natural, that is what you call the bioluminescence. Okay, and regarding actually the conditional material is concerned, then we will have to study little bit, say the principle behind the the luminescence here. So of course everyone knows that actually the luminescence in which actually so the materials are derived by the various energy levels, right? So obviously we know that according to this particular picture, say the slide, then you see that say there are the material absorbs the light at one wavelength, then it lifts the atoms actually to a higher energy state and eventually return to that say lower energy state, and there is the transition between actually so lower say excited state to the ground state, the release of the say emission of the light photon here. So this is actually the simple say behavior about the principle about the luminescence. And so strictly speaking, we will have to follow the Jablonski diagram, right, to explain about the luminescence behavior. And we need to have actually very high say input energy. So this is like actually, so it depends upon the energy. Sir?
Sorry for disturbance.
Yes.
Sir, your screen is not moving, sir.
Is it moving?
No, sir.
No.
Sir, plus the first slide, sir, maximum.
I'm sorry, okay, right?
Sir, first slide, sir.
Oh, first slide is okay. Sorry, sir, okay, right? Yeah, we'll see that. Check. Sir, please actually wait. Sorry for that. We'll check that one. No.
Okay. Okay, sir. Now it's moving, sir.
Wi-Fi the connected.
We will connect as
Nicola connected. The Wi-Fi university Wi-Fi connected.
Sir, just a moment. Okay, sorry for the disturbance. Okay.
Okay, sir.
So there is a net disconnection actually in our laboratory. So
Okay.
Okay. Sir,
Yes, sir.
I'm sorry. So okay. Now it's moving, no, sir?
Yes, sir.
Okay, sorry that actually. So I will go to that the initial slide. So
Sir, screen on the full screen, sir.
oh, full screen varle.
Update out.
So in full screen la sir actually we have actually put in the full screen mode.
Sir, screen stop screen கொடுத்துட்டு அதுக்கப்புறம் மறுபடியும் ஷேர் பண்ணுங்க சார்.
மறுபடியும் ஷேர் பண்ண சொல்றாங்க பாருங்க.
Sir, put in slideshow mode, sir.
Slideshow.
From beginning, sir. From beginning. From current.
இப்போ தெரியும்
sir. இப்போ move பண்ணுங்க sir.
So now it's okay, sir.
Is it okay, sir?
Yes, sir.
Sorry for the disturbance. Okay, I'm sorry. So shall we continue now?
Yes, sir. You can continue now.
Okay, so this is actually that again I want to repeat okay, one or two lines. So this is about luminescence, how actually the smile of the child, we treat this actually some precaution in mind. So we treat this actually for luminescent behavior of a child. And so this actually I put this slide of say holy celebration, and they all enjoy about the festival of say the color. Let me say that the Holi is actually the festival of color. Like that, the luminescent material is also related to the light emission behavior. And Okay, and almost all these kind of luminescence is actually from the firecrackers, especially some kind of a, say, the bushwanum like that. So it depends upon the kind of, say, the metal nitrates or strontium nitrate or barium nitrate, lithium nitrate. It depends upon different elements, and we have a different colorization of the light behavior. And okay, I will skip this one. Then I will also skip this one, right? And directly you go to this, the fundamental, the principle of luminescence, obviously. So in order to understand the principle of the luminescence, we will have to go through the Jablonski diagram. So the essence of the Jablonski diagram is actually, say, the ground state and many excited state. Say the first excited state, second excited, third excited state, that are actually spin state. So generally, the atoms absorb the light, actually the photons in one wavelength, and excite the higher energy state. And eventually there is a transition from actually from first higher excited to lower excited, cross relaxation, and then the atom stay for a certain time and eventually return to the lower energy state with the emission of the light photon, right? So these light photon is actually in this case that needs a very high, say, energy of the absorption. So let us say that, so this is actually how, okay, the high jump or pole vault, right? The person, so put so much of energy in order to lift his body over that particular, say, the line actually that. So that much of high energy is required to lift the atoms from the lower energy state to the higher energy state. And then only we can achieve actually that, say, the kind of atoms in the higher energy state, and depends upon its cross relaxation from various energy states, we will have the different, say, emission lines. So we'll see these details when we discuss about the conditional material. And actually, before going to that of conversion, so as I pointed out, so this is a kind of a luminescent material. Say the ruby laser is nothing but actually certain material made of actually that of a chromium doped aluminum oxide here. So the chromium is actually responsible for actually optical absorption in selectively at two different wavelengths of right, green and the blue. And so in a ruby laser, actually the emission is actually in a red color. So ruby laser is actually, that laser is related to the stimulated emission, the principle. So just I wanted to outline about the luminescent material. So the luminescent material here, it consists of actually the host matrix of aluminum oxide and the dopant atoms of chromium, triply ionized chromium. So like that, most of the solid state materials, so inorganic solid state materials have the host materials of a certain elements of a certain binary or ternary or quaternary in compounds, and in which actually the dopants, either the single dopant or the co-dopants are included in the case. And so before, just I wanted to have an overview about this laser only. So now let us have a look about, say, yeah, okay, right? Yeah. So what is actually the, so we all, the physicists know that actually there are basic differences between actually the lasers, second harmonic generation, then upconversion laser. And how the upconversion phenomena is actually, right, can be distinguished from the other two, the well-known laser principle and second harmonic principle and generation principle in that case. So we all know that, say, laser is actually the light emission, so produced by the stimulated emission behavior, right? But say, obviously, you know that, so lasing emission requires very high threshold pump power. Either it's a 3-level laser or 4-level laser. And depending upon the 3-level or 4-level or quasi 4-level lasers, we know that, say, the threshold pumping power is varied here. But the essence of the thing is that needs very high pump power. So for getting actually the population inversion and stimulated emission. And so the second harmonic generation is also related to certain light emission from certain, say, organic crystal materials or inorganic crystal material like that here. So in which actually, so this also required very high pump power here. So in the case of the second harmonic generation is required by the virtual energy state actually, right? And very high pump power energy is required to create actually that same, the polarization atoms for the frequency conversion. Then what is the advantage of conversion material? So the upconversion materials, unlike laser and second harmonic generation material, don't require that much of a don't require that much of high threshold pump power, right? But this needs actually very low pump power. Very low pump power is sufficient enough. And another big difference between that actually from these energy levels, you know that say there is actually the say two different energy levels. So in this case, actually, there is energy transfer from actually the ground state to the intermediate state and intermediate state to the other the higher energy state. So this is actually, we can say the energy transfer process here. Okay. And another important thing is that the emission wavelength is actually shorter than the pump wavelength here. So the up-converter light energy is much larger than the pump light. So the up-converter light is have a higher energy in energy. That means actually the excitation with the NIR and emission in visible region. So the basic difference is that so lies upon the energy levels, and another thing is depends upon the how the pump power is required. Okay, so up-conversion is nothing but actually energy transfer process, and up-conversion requires very low, say the pump power is sufficient. So even milliwatt of pump power is sufficient. For example, if you want to have a second harmonic generation, we have to have, in case of the KTP crystal, then we have to interact the KTP crystal with the NDAG with the high, okay, so pump power, and so that much of high power is required in the case of the second harmonic generation to give the visible green emission here. Okay, and the concept of up-conversion is actually proposed by the Housel, and the nonlinear optics, we all know that actually proposed by the Bloombergen is the father of the nonlinear optics. Like that, say the up-conversion, the father of up-conversion is material is the say Professor Housel here. And in order to know the full details about the up-conversion nanomaterial discovery and evolution, so you can refer these actually journal here, right? So you can refer the history of up-conversion discovery in that. Okay, and so the thing is that actually here, so this actually ruby laser then and falls on the KDP crystal, then that converted into UV light. So even though here we see that the higher wavelength is get converted into the lower wavelength, that means low energy is get converted into the high energy. But we cannot say it's a kind of up-conversion process, but this is actually defined by the, whereas in this case, the polarization of atoms involved, whereas in the up-conversion, there is no such polarization of atoms are involved, and that okay, then defines by this energy transfer process here. Okay. So as I told you before, then the down conversion process and the up conversion process here. And when you look at that, say the material of choice in the case of down conversion and material of choice in the up conversion material. Say the material of choice in the up conversion materials always actually have certain say rare earth elements like that of a ytterbium erbium or ytterbium thulium. So in which actually the sensitizer material, say ytterbium, and the activator material erbium. Sometimes either the activator material alone get used. But in order to minimize this threshold pump power, right? So we have to supply the energy first to that sensitizer material and transfer the energy to the erbium. And so, for example, in the case of the ytterbium and erbium doped material, then if it get actually excited with the NIR light at 980 nanometer, so that get converted into visible light here. Okay, so this is actually the basic principle of that one. And so what is the advantage of the up conversion material when we compare the down conversion material here? So when you look at that, so this is the conventional luminescence and this is the up conversion luminescence. When we see that the conventional luminescence material, for example, say certain material of choice, say for example, say, so we will have to actually the laser material, let us say that chromium doped, say aluminum oxide, then that is actually excited with the green light, and that gives actually the red emission here. So what is the Stokes shift? The Stokes shift is very small, whereas in this case of up conversion, then so that excited with the 980 nanometer, and then emission is actually 450 or 550 nanometer. So the Stokes actually shift is actually between these wavelength is quite high. So that is actually, that is what you call the anti-Stokes line. The largest shift of the anti-Stokes line. So this is actually peculiar advantage of this, say the up conversion material, because of the large anti-Stokes shift, and say this minimize this autofluorescence in the bio tissues here. So can you able to see that slide moving? Is it?
Yes, sir. Yes, sir.
Okay, right. Yeah. So what is actually the principle behind this actually, that anti-Stokes shift? So as I told you before, so this energy transfer process here. So the first actually that I say that, so there are energy levels are involved, various energy levels are involved. So these various energy levels are defined by this rare earth element in the material. For example, ytterbium actually that has only 2 energy levels, whereas erbium and praseodymium and thulium, there are so many energy levels are in that. For simplicity, we just give only 2 energy levels, and here then ground level and intermediate level and the higher level here. So the 980 nanometer of light get excited and get absorbed by the material, first get transferred to that say intermediate level, and then the first photon, and then go into that say intermediate level, and then this second photon go into the higher energy level. So there is a transition between the higher energy level to the lower energy level in terms of actually emission of the light. So here the NIR light actually say get emitted, absorbed, and then emitted as a say green or blue or a red light here. So it is nothing but actually sequential absorption of 2 or more photons by the say various energy levels here. So the emission wavelength is actually shorter than the excitation wavelength, and that is what you call that anti-Stokes emission. And this anti-Stokes emission is actually an interesting characteristic of a up-condition material, and this gives actually very good effect in biotissues. And one is actually absorbing wavelength NIR has high penetrating power, and NIR to visible light has a large anti-Stokes, so minimal autofluorescence. So these are the anti-Stokes emission, minimal autofluorescence, high penetration in biotissues are the advantage of the up-condition nanomaterial here. Okay, so this is actually the picture that I put up. So how the energy levels are involved here. So these energy levels are related to the ladder-like energy levels. How actually the okay. So we go to that higher say the state actually in mount or hills or something by using the ladder like that, whereas the materials have the ladder-like energy levels. So this get pumped from one level to the other level and other level to the next level, then to the higher level, then eventually we have to come down to the lower energy level. So this is nothing but actually ladder-like energy level. So energy transfer process is there, that is excited state energy transfer process there. Then 2 or many photons are involved in the energy transfer process. So these are the characteristics of a up-condition material. And so there are various kinds of actually up-condition. The principle is there. So one is actually excited state absorption, energy transfer absorption, photon avalanche, the cross relaxation, then cooperative energy transfer process, and so many actually the energy transfer process are there. But most effective the up-condition emission is actually by means of the energy transfer up-condition. That is by means of there are 2 different material. Whereas in the case of the excited state absorption, we have only one particular ion, say for example erbium alone. Whereas in this case, energy transfer up-condition, we have 2 say ions, that is metal ions like the ytterbium ion, then erbium ion, or erbium, or you can just substitute with certain say other kind of element like thulium or praseodymium. So we can experiment with the quite a lot of actually the ion. But most famously regarding the up-condition nanomaterial is concerned, we use actually ytterbium and sensitize with erbium, thulium, or holmium like that. Let me see in details later here. Okay, so let me have a small actually discussion about only these 2 such a excited state absorption and energy transfer up-condition process. So then and there I just put actually certain references. You can please note, and these references are much highly useful to know much detail about right. So these are up-condition, interesting up-condition nanomaterials. So you can just see these references in the, as well. Okay, and so either we can say that it is actually ground state absorption or the excited state absorption here. So these are all actually various processes are there. First, actually, let us say that say erbium, right, or holmium or thulium have ladder-like energy levels, and these simply actually doped erbium, holmium, thulium doped material that is called that say ground state absorption or the excited absorption process. Say mostly the erbium doped glasses materials or erbium doped barium fluoride like that of the materials are so many varieties of materials are there. Here the excited source actually be provided with the high pumping power. Please note that say if we have only one particular ion in upconversion, then that required very high pump power. So the excited state absorption is not easily absorbed, and there has to be actually modified with the energy transfer upconversion process here, right? And so what is the advantage of energy transfer process? Say the energy transfer process, as I pointed out earlier, so this has actually two different metal ions, lengthened ions here. So one is sensitizer ion and another activator ion here. So let us have a close look about this material. Varieties of the materials are there, but for example, here we use actually sodium yttrium fluoride doped with ytterbium and erbium. So these actually various compositions are there, and mostly because actually the ytterbium is there, sensitizer, then that consists of 20%, and erbium it may be around 2% or 1% like that. So why we have to have a 20% ytterbium? So we have to have a very high energetic absorptions of the NIR light, and these have actually absorption cross section, very high absorption cross section, and the atomic content is quite high, so easily get absorbed more number of photons actually from these ytterbium ion. And when you look at these energy levels of this ion 1 and ion 2, that is ytterbium and erbium, and erbium, say these metastable level, so first exit level is almost closer to that, say ytterbium excited. So what happened? There is an energy transfer happen because so these two levels are actually closely at the same energy level. So there is a resonant energy transfer is possible. So one photon actually transfer to that and then exit the higher energy state, and that fills actually that. So the higher energy state, then it return to the ground energy state with the emission of the, say, the green emission here. Say NIR emission to the green emission happened here. And like that, say here, erbium also absorb the, say at 980 nanometer. But the absorption cross-section of ytterbium is quite strong for 980 nanometer, whereas absorption cross-section of erbium is very weak. But this has strong absorption for 1150 nanometer alone. Okay. So there is a efficient energy transfer, right, from ytterbium to erbium, and then ytterbium mid-level to the higher level here happened. So there is a energy transfer of conversion happened here. So this is the advantage of actually the energy transfer of conversion. So interesting actually, faculties may please refer the concerned say literatures as a point out here for getting more details about that. Okay. And so I visualize actually the energy transfer of conversion is related to that, say the, okay. So there are actually two different actually the ladder-like energy level. So this is a ladder-like energy levels here. So two pet actually cats, say the first actually jump from the ground state to the other, and then say this cat actually, so these levels are almost on the same level. So what happened? This photon actually, that means I assume this actual photon here, then they transfer to this one, and this go to the higher energy level. So eventually returns down with the emission of the green or blue or red. That depends upon that. So I just visualize actually these so ladder-like energy levels related to that, say upconversion nanometer, especially in the case of the lanthanide doped materials like erbium or thulium or holmium here. Okay. So if you visualize this one, and it will be easy for you to remember how there is a energy transfer process happens and how it actually activates the materials in the second ions to give the emission, the upconversion emission here. And obviously, say we see that, so to some, say NIR excitation, and so NIR excitation here that gives, say, visible emission like that. Okay. And the first upconversion material actually quite long before in 1960s was investigated with the use of actually lithium yttrium fluoride doped with the erbium 3+. So in which actually then they have used this as upconversion laser material. So in the first actually the material that is investigated in 1960 by Professor Hauser used this material is concerned, and in which actually they have this actually only one singly doped ion here. As I pointed out that, so this require actually ground state absorption or excited absorption. So this require very high pump power. So let us have a look on that pumping. So with the case of titanium sapphire laser. So titanium sapphire laser is a vibronic laser, and this gives actually very high energetic, say, lasing light output. So in order to have the upconversion light emission in singly doped erbium doped lithium yttrium fluoride, that time they have used titanium sapphire laser to pump this erbium atom, and that time only they get actually the very weak emission here, the blue-green upcondition, but it's a very weak. And that time they have used the crystal material, okay, the single crystal material, and later then they modified actually that, say, instead of lithium yttrium fluoride, then they code up with the ytterbium erbium, and then they get actually blue-green emission, but with a slightly less pumping power. And during the time of investigation of the upconversion laser, they have used the crystalline material. But nowadays, with the advent of the nanotechnology, the people have explored actually the how one can use the upconversion material for, say, nanoscale, say, photonic material. Okay, so this particular advantage, why this particular photon upconversion nanomaterial becomes quite interesting. And nowadays, this is because actually, so 980 nanometer excitation wavelength. So these 980 nanometer excitation wavelength can be actually accomplished by means of the simple diode laser. Okay, so just like actually how the green diode laser or blue diode laser or red diode laser, like that we have actually, say, the indium aluminum gallium arsenide, like that, say 980 nanometer based diode laser here. So these 980 nanometer diode laser is a small handheld, say, laser. Okay, please bring that one. Just a moment. Emission Virda. Sorry, okay. So I will actually give a small demo. Yeah, okay. So this photon upconversion was the first actually studied in bulk crystals, and later is actually going to that, so nanoscale materials. And nowadays actually so many materials are there, and these mostly use actually fluoride materials. And why we mostly use the fluoride materials? Because oxide materials are actually so has a high the phonon vibration here, whereas the fluoride materials less phonon vibration, so that we can have a very good say the narrow the line width in the case of the fluoride host material, whereas oxide materials always have the very wide actually the line width, very broad line width, whereas in the case of fluoride host materials we have narrow line width. That is the advantage of that, say, the fluoride material. So the fluoride upconversion based host materials are most famous in, say, the upconversion material here. Okay, and so the characteristics of our upconversion materials are, as I pointed out, anti-Stokes emission. So because of the anti-Stokes emission, then there is actually wide actually that wavelength difference between the excitation and the emission lines, maybe around say 50 nanometer or even say 100 nanometer or even 400 nanometer, depends upon low autofluorescence and sharp absorption emission lines and high quantum yields, that is high intent, long lifetimes, a very good photo stability, and low phonon energy in the case of the fluoride material. And because of these advantages, we can use actually this material for the same the bio application here. And this periodic table shows that actually so most famous actually upconversion materials are derived by means of that, say, the alkali materials or alkali earth material here, and this, for example, sodium and transition material yttrium with certain fluorine group here. So we have to choose a material and actually that okay, the alkali earth and alkali material here, and then the fluorine material, sodium yttrium fluoride or lithium, say, yttrium fluoride, or okay, in this case potassium yttrium fluoride, or let us say that barium yttrium fluoride, like that, or calcium yttrium fluoride, or sometimes you see that calcium fluoride doped with ytterbium erbium, and so many choices of the material. And these are doped with rare earth material like mostly, say, ytterbium, okay, then thulium, then erbium, holmium. So these are the most material, but we also experiment with other materials as well, dysprosium, but we are not able to successful in getting actual upconversion regarding the dysprosium material, and we have used gadolinium as well, right? So depending upon actually that, say, if you have a clever knowledge about the, say, the periodic table of elements, and we can play with quite a lot with the, say, designing so many new kind of, say, upconversion materials here. Okay, and as I told you before, then that requires actually the sensorizer atom and then activator metal atom here, right? And regarding this particular thing is concerned, as I told you before, this actually sodium lithium fluoride. So this, when you look at that, actually that of the unit cell of a particular, say, material of a conditional material, say, let us say that, say, these are all corner atoms are occupied by that, say, host atoms, say, for example, right, sodium lithium fluoride in this case, and that are actually doped with certain ytterbium and erbium. So let us say that this brown colored is actually ytterbium and the green color is the erbium here. What happens, as I told you before, so this absorbs the 980 nanometer radiation. So this absorbs the 980 nanometer by ytterbium and transfer actually to this, say, erbium here. So there is an energy transfer from ytterbium to the erbium. And if we have 20% of the ytterbium, then that lattice is actually get mixed with the so many number of actually the ytterbium atoms. And so it depends upon the close proximity of ytterbium to erbium, then the energy transfer will be there. Say, for example, if we have erbium of ytterbium of 20% and erbium at 0.1%, there is very less number of actually erbium atoms are there, and this may be get displaced to a very long distance. So then energy transfer maybe get minimized. So efficient energy transfer will be get minimized, and hence the final quantum yield get also minimized. So the proper choice actually we have to have a appropriate actually the ytterbium sensitizer atom, and we have to have appropriate, say, erbium ion concentration. And accordingly, you see that according to this particular lattice, then you see that ytterbium to the erbium, then the green emission, and like that, say, the ytterbium to erbium. So the redemption is also possible here. And say sometimes actually, if the material has some kind of water molecule, these water molecules are get absorbed by that. So it will suppress the luminescence emission. So we will have to have a very good quality, actually, highly crystalline material, right? So sometimes actually the water molecule get absorbed the light. So there is energy transfer from ytterbium to erbium. So this particular lattice, okay. So the schematic illustrate about how the upcondition, say, energy transfer happened, how the upcondition energy related to the certain emission behavior in that. Okay, so this is a kind of actual that sodium lithium fluoride doped to ytterbium erbium. When you note that, so this is a small actual handheld laser pointer, and let us look that this is a 280 milliwatt. When you compare with the second harmonic generation, absolutely we are not able to get, right? So second harmonic generation emission with the small actual 280 milliwatt. So several actually, say, megawatts of say energy is required for polarize the atoms which has a second harmonic generation. Like that, in laser also we have to have a very high pump power, right? So whereas in the case of conversion, we have very little actually the pump power is there. That is the advantage of that. And we see that the emission is actually, so because of erbium that gives the green emission, because of thulium that gives the blue emission here. And I want to demonstrate actually the small things about, okay, my student actually here, and he will demonstrate, right? And the light emission from, can you switch on the light? Yes. Yeah. So please actually, sorry. So can you able to see something here? Can you able to see that, sir?
Yes, sir. Yes, sir. This is visible, sir.
Yes, sir. Yes, sir.
So these are all actually the material. So just I will switch on the light. I will switch on, please. Okay. Now you show actually what is the laser here. So only this is actually handheld laser. Yeah. So can you able to see, sir, this one?
No, sir. The slide is not visible, sir.
Not the one laser pointer. Can you able to see the laser pointer? My
No,
student
sir.
is holding the laser pointer.
No, sir. Not visible, sir.
Okay, just a moment. Okay, I will. Sir, can you able to see?
No, sir. The slide is not moving, sir.
No, slide. No, sir. Actually, please actually see the my photo there actually there. My image இருக்கு இல்லையா? என்னோட இமேஜ்ல பாருங்களா, not in the slide.
Okay, sir.
So in the slide
Yes, sir.
பாத்தீங்களே, அந்த slide என்னோட இமேஜ்ல பார்க்கும்போது there is one particular say laser pointer. You see that?
தெரியுது sir.
So this is actually 980 nanometer laser. A handheld laser pointer. Yeah. So a small laser pointer, just like a pen size actually that. Right? So now this is actually up-conditioned nanomaterial. So we have the up-conditioned nanomaterial. Right, sir? Can you able to see the green light here?
Yes, sir.
Yeah. So say, so this lower side actually, not in upper side. So that small particles are actually just are sticking on the walls of that cuvette. The small, even a small actually, minute actually particles are sticking on that will also give the emission. So at the lower side, you see that at the lower side there is a up-conditioned nanomaterials there. So when actually this 980 nanometer light, okay, laser light, this is the laser light. So that interact with this say up-conditioned nanomaterial, then there is an energy transfer and it gives a green emission here. So like that, do you have the blue sir? Blue emission? So just a moment, sir, actually. Just I wanted to give a demo of about our nanomaterials. So you'll be able to see that. So even we can do this kind of work even in laboratory. And so this is the kind of actually spectroscopy, up-conditioned spectroscopy related things that. So we will see actually how we can visualize actually by use of spectroscopic techniques later. Red emission. Okay. So sir, this is actually one another material. Sir, can you able to see this? Sir? Oh,
Yes, sir. Visible, sir.
Okay. Just a moment. There is net problem here. So just okay. I will demonstrate my slide here. Yeah, okay. Yeah, sir, please actually see this small vial and in which actually the material is there, up-conditioned material. So can you able to see the red emission from this?
Yes, sir.
Yeah. So this is the thing that I wanted to demonstrate from our material, the synthesis in material. So even this actually powder material, we can, for bio application, we have to make it as a water soluble, completely water soluble material. Okay, thank you, Ajit. So he is my actually PhD student and many students have worked on that. So this kind of material, then they have fabricated this up-conditioned material. Now I will switch over to the slide mode.
Sir, kindly share your screen, sir.
Yeah, okay, now. So now you look at this, sir.
Share பண்ணல.
இதுவா?
Zoom meeting போட்டு share பண்ணனும் sir. Screenshot.
Share it, sir. Sir, can you able to see this?
Yes, sir. Yes, sir.
Yeah. I hope now you understand about this one, right? I hope everyone understand about how the behavior of a.
Yes, sir. Yes, sir.
Yeah. So this is actually no secret. This is open secret actually, right? So we can, everyone can prepare this material in the lab, the simple facility. I will show actually some demonstration how one can synthesize the materials. These are all chemical based synthesizer. So even though we are in physics actually, then we can adopt some of these material science route actually to prepare this material here. So we have demonstrated our own material with the kind of 980 nanometer, so give green emission and the red emission. Like that, we also have the material that gives the blue emission as well here. Okay, so And these emissions are characterized by, say, these various energy levels here. Let us have a actually energy level diagrams about the various luminescent, various rare earth material. And our choice is actually here, the erbium here. And the advantage of erbium is actually only two energy states are in that energy levels that is defined by 2f 7 by 2 and ground state and 2fy the 5 by 2 here. And we can code up the material with the erbium. When you look at this erbium level here, we see that there are actually so many energy levels here. Okay, so there are so many energy levels here. And when you look at this 2f 5 by 2 and for a 11 by 5 by 2, then there is energy transfer from this will happen, and hence actually we have the emission in various colors that ranges from blue and green, mostly green and red emission here. Like that, if we have the holmium, then we have the energetic blue emission and as well the green emission,
Sir?
red emission there.
Sir,
Yes,
sir, the slide is not moving, sir.
slide more there. And one more thing, sir.
No, sir.
Oh. There is a problem there. Now it's moving, sir.
No, sir.
Please, actually, sir, wait. There is some problem with that. Actually, I don't know what happened. My student is assisting. Sir, okay, we are rectifying. Please, actually, sorry for the inconvenience. Please.
Okay, sir.
Sir, is it moving now?
Yes, sir.
Yeah, okay.
Now it's clear.
Yeah. Okay. So there are actually various energy levels are involved. Anthenide material. Accordingly, there is different emissions behaviors in that case, right? And so like that, actually, we have several kinds of materials, so in this case of a thulium doped actually blue exponential lasers, then we have the pumping around the 1120 to 1140 nanometer, and in this case the emission is around the 480 nanometer if you only use thulium. But if you use the ytterbium with the thulium, then we no need to use this pumping, but you can use the 980 nanometer itself in that case. And like that, actually, in the case of the erbium doped material, code of the material, then we have the erbium ytterbium absorption 980 and emission at about, say, the green region here. Like that, say, we can also presodium then dope with ytterbium, then we can pump with another, say, light at 850 nanometer, right? And this gives the emission at actual orange, green, blue, and red here. So there are varieties of choices of actual luminescent emission can be accomplished by using cleverly selecting suitable sensitizer and activator element here. Okay, and so this is the case actually in the case of the ladder-like energy levels. When you recollect actually some of the things that I explained in the initial slides, and there is energy transfer process happens. And let us have some examples of sodium yttrium fluoride with the ytterbium erbium. So ytterbium forced to absorb this light at 980 nanometer, and there are various ladder-like energy levels. So these are 2f5 by 2 excited level of ytterbium and 4i11 by 2 of a level of erbium are almost closer to that. So there is energy transfer happened from this level to this one, right? And like that, there is actually energy level transition actually from, say, the erbium also. Then there is a transition from actually 4i11 by 2 to this 4s3 by 2. And like that, actually, there are, say, excited energy levels are there, and cross relaxation to the 4s7 by 2 to other 2h11 by 2. And so this gives actually the transition a green emission. Like that, say, there is another cross relaxation actually from, say, 4f7 by 2 to this actually So for yes 3/2, then there is another green emission here. And like that, say there is a transition cross relaxation from say 4 of 7/2 to then eventually return to that, say 4 F 9/2, and hence you give the red emission here. So depend upon this the transition from one higher level to the other lower say levels, say we have the various energy emission in this case. Like that in the case of the ytterbium and thulium, we see that we can have the thulium, say in this case blue emission, dominant blue emission like that. And in the case of the holmium also, we have actually that of a say green and red emission here. Sometimes we have the holmium is actually say magnetic properties, so depends upon this choice, we can make as a core material or shell material, or we can make as a core shell material. And how we can use this material for bio applications like that, right? So there are various applications of this subconduction. So mostly is we employed in say biomedical applications, and sometimes they are used in solar cell applications, and they are investigating for sensor applications and the fingerprinting, say for example forensic sciences. So they are using that case, and say in order to verify the fake currencies to original currencies, so they are using the upconduction nanomaterial. So this has a very wide application in so day-to-day life as well. So regarding these actually bio applications like that, as I told you before, so upconduction nanomaterials are useful for bioimaging, that is by using multiphoton excitation in air light, and so we can make these upconduction nanomaterials as a carrier, nano carrier. So we can load the drug at the surface of the upconduction nanomaterial by linking with certain, say, the surfactant, or by linking with the certain other, say, ligands in this case. By linking these drug molecules, upconduction through this ligand, and so we can use this drug nano carrier here. And the same upconduction nanomaterial can be useful for the photodynamic therapy. So we can first functionalize this actually the upconduction nanomaterial with the help of say certain dye molecules. There is energy transfer from upconducted green light or red light to the say dye molecules, and hence this itself will give the dye molecule gives certain say redox oxygen, and this redox oxygen generation kills the cancer cells. And apart from that, say the upconduction nanomaterial by the illumination of the 990 nanometer light that heats up the say cancer cells actually to a certain higher temperature, about 45 degrees Celsius. So simultaneously, what happened? These upconduction nanomaterials, upon interaction with the 990 nanometer, heats up the cancer cells and kills the cells, and as well the redox oxygen also kills the cancer cells. And sometimes we can, when they load the drug, so this specifically at the say cancer cell, we can introduce this drug molecule in that. So these multifunctional activities of the upconduction material. So we can say it is a multifunctional material. And sometimes we can use this as a photothermal therapy. So we can functionalize these upconduction nanomaterials with the drug and a certain dye molecule and say ion molecule like that, ion oxide. So these ion oxide are being useful for the photothermal therapy. So one can use these actual upconduction nanomaterial for multifunctional applications like that. And sometimes we can use the bio sensing. When you look at this particular slide that illustrate actually how these upconduction nanomaterials give certain emission in red color or green color, right? Like this, green and red or blue, and we can load this drug onto that. So we can specifically make this nanoparticle to inject through the veins at a particular site, or even say, for example, in the case of the skin cancer, say by injecting this upconduction nanomaterial loaded with the dye molecules and drug specifically at the skin cancer point and illuminate with the 980 nanometer laser, then we can use it as a photodynamic therapy purposes. And this is theranostics means actually both imaging and treatment, cancer treatment here. So one can use this nanomaterial loaded with the drug molecules, right? So we can use it as a cancer treatment purposes. So because of that multi-advantage of that upconduction nanomaterial, biologists are using this one. And these particular upconduction nanomaterials are scarcely actually experimented and investigated in our country, whereas in case of the European countries, many researchers and they are using this conditional. In China, there are lot of actual the research laboratories are there. They are using in Russia. They are using that. So mostly these unconditional materials have been explored for varieties of bio applications in, say, European. There is a separate European network for unconditional is there. So different universities actually, okay, linking with the different researchers, and they're collaborating with the various researchers, and they're doing very wonderful, say, the unconditional nanomaterial research for various bio applications in that case. But in our country, and we don't have that kind of network actually, right? So in each and every field, that is that pathetic situation in India. Okay. And so what are the other advantage of actually, right? So NAR light here, because we know that unconditional means here in the case of that we use so NAR light. What is the advantage of the NAR light when you compare that? Say we have actual quantum dot. So the quantum dot absorbs at lower wavelength, say for example, say ultraviolet light and emits in visible light, or quantum dot sometimes some quantum dot absorb visible light and emission in visible light. It's also absorption and emission both in visible light. So what happens? So in the case of the quantum dot, or in the case of actually conventional down conventional phosphors, so these have actually very small actually that of the Stokes shift, and because of a very small Stokes shift, then say high autofluorescence. We cannot visualize actually, we cannot differentiate actually the so both the emission and the absorption lines from the same the site in the body tissue. So that gives actually quite a high autofluorescence, whereas in case of the NAR light has the say low autofluorescence, and and whereas in the case of the conventional luminescence actually high tissue scattering, whereas the say this NAR has actually for low tissue scattering and low tissue absorption, because the 980 nanometer light is not get absorbed by the water molecules, so low tissue absorption, and because of these advantages, so this has been used in biological window, let me say bio window like that. So almost all the physics the faculties, and we know that optical say transmission telecommunication window like that, say how the optical fiber when it actually be illuminated with the 680 nanometer high loss, when it actually with a say medium communication, say we use 1330 nanometer, their second optical communication, and another optical communication, long distance communication, we are using 1550 nanometer, quite low loss in that case. So we can use it for the long distance optical communication like that. In this unconditional nanomaterial, if we use this kind of NAR light in this case, we have the low loss and low autofluorescence, and we are exploiting this use of advantage of NAR light absorbing behavior of unconditional material. So we use it actually for say various biological application, high penetration in the body tissues. That is the advantage of actually the unconditional nanomaterials for bio application here. Okay, and so just I wanted to focus on some of these actually material synthesis, and so this material synthesis, then in our laboratory we use actually hydrothermal method, thermal decomposition method, co-precipitation method, microemulsion method. So most of the faculties, those who are a good research experience, knows well about all these methods. I don't need to explain much more in detail, but however, I want to point out how we can use it actually, right, for these various applications. And you please actually see this particular recently published review article, right, on lanthanide doped in iron product active unconditional nanophosphors. Then they give a fundamental concept, synthesis strategies, and technological applications. There another one, Professor Venkatakrishnan is working in IIT Mandi in Himachal Pradesh. He actually one of my the students of my actual friend. Now he is a faculty in IIT Mandi here. Okay, and so the unconditional nanomaterials, say lanthanide dope specifically. So chemistry people use actually their own actually triplet to triplet annihilate actually 2 photon based unconditional. So they use organic material for that. But say I am interested in lanthanide dope, the inorganic nanomaterial unconditional. So these lanthanide dope, the inorganic nanomaterial synthesized, and we can modify it by using the various ligands or various biomolecules, and we can load the drug, and we can use it for the bio applications, and say we can modify the synthesis strategy by then we can enhance the luminescence, then we can use it for the bio imaging and as well for the solar cell applications here. Okay, and this is one such actually that of a material that we have prepared in our laboratory by using the simple, say the so autoclave. Then we just mix with the say yttrium nitrate, ytterbium nitrate, and erbium nitrate with the certain sodium ammonium fluoride. Say, or here we use the lithium fluoride all mixed together and stirred, and then transfer this colloidal solution into the hydrothermal vessel, and allow it actually heat for about 180 degrees Celsius for 24 hours, and we are able to get actually very fine actually different size of the crystals, tetragonal the crystals here. So these kind of tetragonal crystals gives actually emissions in both green and red emission, and we also investigated for solar cell application, but I am not focusing on here in this case, right? And so recently we are using actually we are preparing this upconditioned nanomaterial by thermal decomposition method. So in the previous case actually the hydrothermal method just actually, so we form actually nucleation of this particular application upconditioned materials at a particular say time, whereas in the case of the decomposition method we decompose the acetate precursors of these say the lanthanide precursors and right. So say for example, so in this case ytterbium say acetate and erbium acetate. So these acetate, whereas if you use actually salts like a nitrate salts or chloride salt, this has a lower so decomposition point, whereas the acetate precursors of the ytterbium and erbium has a very high the decomposition point. So one can able to synthesize the material at maybe 300 degrees Celsius or 250 degrees Celsius, and even we can make a say somewhat a crystalline material, right, even at the say colloidal state itself. And whereas if we use actually chloride material or what is the nitrate material by using say what is that conventional co-precipitation method, this only forms as amorphous material so that we cannot get a good emission. But in the case of a thermal decomposition method, because we prepare this material at very high temperature of about 300 degrees Celsius, it eventually forms as a nanoscale crystals, right? So these nanoscale crystals that formed at a 250 degrees Celsius decomposition point, that gives actually very good emission here. So, and another advantage is that, say, if we use actually co-precipitation method or say hydrothermal method, so this gives actually the powder form of that material. Then we cannot make it further as a water soluble molecule. But in this case, we can make it as a water soluble by the thermal decomposition. So directly we can use it actually for so biological application here. But this needs actually certain say inert gas atmosphere. So we can make it actually, this is a simple say reflux condenser, and with a certain small nitrogen cylinder, we can make this a small setup in one laboratory within about cost of about 10,000 rupees itself. We can make this material. We can make this setup in our laboratory here. And advantage is that if we make a colloidal solution of this actual upcondition by using thermal decomposition, we can have the monodispersed particle like that. Okay, so that is the advantage of this one. When you look at the scale bar, it is about 100 nanometer. So this is a hexagonal nanoparticle. So you see that the particle size may be around 15 nanometer. Nowadays, actually, people are concentrating actually to prepare this upconditioned nanomaterial sub-nanoscale. Say, for example, 5 to 10 nanometer scale, say the nanomaterials they wanted to prepare. So this is a research activities going on in preparing 5 to 10 nanometer size upconditioned nanomaterial for biological applications. Okay, and so this schematic picture illustrates actually. So this is a 3-necked flask actually that is a say reflux condenser. Then we have actually a rare earth precursor, that means erbium acetate, then ytterbium acetate at a particular composition, and we also have sodium acetate, and we have the solvent of actually oleic acid and oleamine and dodecane here solvent. And in this solvent actually we disperse actually all this acetate and heats up and slightly to about 1 hour, and then you see that the high temperature and this get decomposed to form actually nucleated sites of actually sodium yttrium fluoride with doped with ytterbium erbium. So this is the advantage, and depends upon actually that reaction time and temperature and the kind of the ligand. Then we can prepare the several kind of actually material with the different actually the improved actually luminescent property or minimal the minimal nanoscale material here. Okay, and so this is the thing that I told you before, and so the synthesis strategy actually by use of the surface modification here, and when you look at that, actually we can use actually upcondension nanoparticle as I pointed before. We can just functionalize the dye molecule, and we can use this kind of for photodynamic therapy, and sometimes we can use it actually for iron oxide nanoparticle, so we can use it for the photodynamic therapy. So sometimes we can functionalize the certain plasmonic actually the particle like a silver or gold. So a simple sodium yttrium fluoride erbium nanoparticle, okay, can be functionalized with a suitable same the surfactant, then loaded with a drug molecule or dye molecule or iron oxide molecule or plasmonic molecule. Then so even like a folic acid receptors, and so we can use it for the very wonderful different kinds of application like that of a say photodynamic therapy and various other cancer therapeutic application here. So this is the thing that I actually copied from this website. Mostly these Chinese are working so hard, and they are developing quite good number of materials for that. And another one is actually I no need to go in detail about this cold precipitation method. Okay, I will skip this one. Okay, and this also I will skip actually because one of my students has worked on that. This is somewhat actually tedious process of preparing micro emulsion, and so in which actually this oil in water like emulsion here. So we know that actually oil cannot be mixed with the water, but at say one particular composition, say by using suitable say chemicals, then we can have a say miscible oil in water like solvent here. So first we have to prepare the solvent, that is a microemulsion solvent, that is by using water in oil like actually microemulsion solvent, in which actually we can disperse these kind of rare earth elements of ytterbium erbium and host elements like ytterbium nitrate or the sodium fluoride. Then so we can have a same upcondension nanoparticle, right? So the thing is that say upcondension nanoparticles say that here we just actually colloidal actually the particles, and finally when we heats up the material, then this forms of the cluster like material. Then we are able to get actually say the crystal get actually needle like crystal growth from the interface and forms not only the spherical particle but as well we have formed a needle like particle. But this is actually initial time of the first initial time of the preparation, then about say 8 years before, and so that time we are not actually concentrating on biomolecule, then we are just to focus only on preparing the material. So we have calcined this prepared material to very high temperatures, about 300, 400, 600 degrees Celsius. And those materials that are calcined at 300 and 400 gives only the cubic phase. The cubic phase is actually weakly, okay, upconverting material, whereas when you heat it actually 400 to 600, then that gives actually hexagonal particle, then gives a high intense light emission is there. Okay, and these are all the so the clusters of actually that of particles are formed. And when you look at this scale, right, it is a 500 nanometer. When you actually split this actually scale into tiny one, then this one is actually about 15 nanometer. When you closely look at this 15 nanometer, you see that the particle size is about 15 nanometer here. So we are able to okay get actually nano clusters of conventional particle contains a small say nanocrystallites in this, right, of 15 nanometer. And when you heat these materials at a high temperature, we see that we are able to get actually nano certain rods like that. So these nano rods are acting like a light pipe, and hence we can able to tune the light actually from red to the green here. So in this case, the nanocrystals comprise of a very high intense the green emitting light here. So this is actually one of my students, actually Dr. Gunasiran synthesized. Now he is working in IIT physics department as a postdoctoral researcher, and he is using this material for now exploring the optical trapping studies of our biological molecules. Okay, and Okay, so apart from that, we also made a multifunctional materials like that of sodium gadolinium fluoride. So instead of actually the yttrium fluoride, so we incorporated gadolinium. So this gadolinium is a paramagnetic species, and this paramagnetic species is actually useful for the MRI imaging here. And so they also functionalize with the silver, and the silver is actually plasmonic particles. These plasmonic particles not only enhance this upcondension emission, but as well, this silver has the X-ray absorption property. So we have used actually for the CT imaging also. So we have used actually this multifunctional sodium gadolinium fluoride doped with ytterbium erbium functional with the silver, and we investigated actually for cancer cell bioimaging and other multifunctional imaging like MRI imaging and CT imaging like that. Okay, so we have investigated this material, and if we load actually some doxorubicin cancer drug, we can use it for the therapy purpose. And we published this work in a microchemical actor is very high impact factor journal of about 6.5 like that. So we took a very hard effort to publish in this one. Okay, and so this actually this material have been prepared by using the polyol method. Okay, by using PEG. This is because we wanted to prepare actually silver nanowires like that. Okay, so not like a spherical particle, not like actually rods, but we wanted to prepare silver nanowire. Then hence actually we use the PEG by using polyol, and the silver is actually formed as a wire, nanowires over this particle here. So this is silver nanowire. These are the silver nanowires, and these acting as a plasmonic nanoparticle like that. Okay, and conventional, as we seen that actually we experimented by using X-ray diffraction studies. No need to explain because I have limited time. And the important thing is that the thing is that actually we have to investigate these prepared particle by using either it is a form of amorphous or crystalline, or either it has been formed as a cubic or hexagonal like structure or mixer like structure. If it is purely formed as a hexagonal like structure, then the emission property will get varied. If it is cubic, the emission will be of a low quantum yield. If it is mixed phase of cubic and hexagonal, this also affect the emission behavior here. So we should be very precisely synthesize the compound. We have to carefully heat the material to have them the hexagonal phase. Otherwise, so we cannot get the good emission behavior. And so we can say that by spectroscopic examination, then we can find out in which emission, in which absorption the wavelength is that. Then it shows that 980 nanometer absorption here. And this one sees that actually that the 980 nanometer absorption, then the emission will be at actually so green and red emission. By using actually erbium, by functionalize the silver, then we have the tuning the light from intense green to the intense red here. So you can make it as tunable nanoparticle as well. Okay, so I don't need to discuss because I have limited time here. So just and so what are the other important applications of these? So just a moment. Okay. Yeah. So important application of conditional nanomaterial. As I told you before, it is actually NIR light emitting NIR absorbing behavior. Okay, so NIR light interaction, as I told you before, NIR light interaction leads to high penetration in biotissue. Okay, sorry, okay, just a moment. So NIR light has a high penetration in biotissues. Let me visualize actually this one. This slide shows that. Okay, so absorption behavior of actually the light of different wavelengths, and here we are all using actually the various lasers itself. Okay, so this, for example, UV laser, exam laser, and so this kind of organelle laser actually at about organelle laser actually 488 actually blue and green emission. Then environment generation visible light, and so this ruby has a red light here. So this is the schematic diagram of the skin, right? So when you look at that, the penetration, which one has the high penetration power here? So UV has a not much actually larger penetration. Whereas when you compare this red, actually this goes up to the certain blood dermal vessels in the say the skin here. Whereas in the case of say 980 nanometer, let us say that this has a longer penetration here. So the advantage of actually 980 nanometer or NIR light is that very high penetration in the body tissues here. And so when we have actually the subconditional nanoparticle get injected into that of say body cells, so at a specific cancer site, actually we can make this light get focused at a particular specific site. So it passes actually through these various layers, say the skins, and eventually goes into that particular cancer cell because of the high penetration power of that one. And I wanted to give a small explanation about the illustration about the a high penetration power of the NIR light here. And so let us have on this slide, and this is actually the wine cup and wine bottle here, right? So in this case, actually the wine bottle here and the wine light cup here, this actually illuminated with the visible light here. Okay, so when his light is illuminated with the visible light, whereas the same actually illuminated with the visible plus NIR light. So you see that, so this gives actually the certain the transparent. That means actually this NIR light actually get transparent towards this one, right? And same, if the completely we use this NIR light, these NIR light get completely transmit this in so high penetration power of that. This shows actually the high penetrating nature of that say light here. So that's this is another advantage of a NIR light. Say for example, in the case of that defense application, they are using the laser rangefinder. So these laser rangefinder they are using actually NIR light based laser rangefinder because during winter season or fog, say they can easily able to see that. Okay, so without any difficulties. That means actually NIR light has high penetration power. It does not get absorbed the water molecule, so it get high penetration power in that. So because of that, high penetration power of the NIR light, so we have actually good advantage of using these unconditional nanomaterial for various bio applications here. And so this is actually if NIR imaging allows to look through the red wine here. NIR imaging allows to look through the red wine here at this particular point. So this shows actually. So I just copied this information from optics and physics of NIR imaging from this SPA proceedings of paper here. So you can refer to more details in this. And this actually schematically, graphically that illustrate about the NIR absorption behavior. And you see that the high penetration power, and let us look that one. So this region, say it is about 980 nanometer. This is the first biological window. This is the second biological window, and this is the third biological window. And nowadays, actually, people are moving towards the third biological window. And when you look at this one, this actually 980 nanometer. So this has high, say, a light absorption here and low scattering as well. Whereas in the case of visible light, high scattering. So if we use a conventional, say, quantum dot or conventional, so nanophosphors for bioimaging application, this induces actually a lot of scattering, then that gives actually high level of, say, the decrement in the, say, contrast visualization of the imaging, right? Whereas in the NIR particle, so based conditional particle have actually low scattering and low autofluorescence. So one can easily get a very high contrast image of the cells. That is the advantage of this NIR light based conditional material. So this actually, so effective penetration of this, right, NIR light is quite high in conditional material that doped with the ytterbium ERPM. So this is the advantage of that one. And so, okay. And yeah, nowadays actually we are using this pulse oximeter, this COVID right season. So every time, every year actually. So during actually February, so this what is that? COVID also celebrate Valentine's, right? So it comes and this is actually Valentine, want to celebrate Valentine. So every time actually celebrate actually in India. So February is the peak time actually regarding the COVID. And so we are using actually this kind of pulse oximeter. So this pulse oximeter uses actually that, what is the principle behind of investigating about oxygen levels and by that using actually two different actually light sources. One is LED light source and NAR light source here. So what happened here, there are actually that light actually goes into that actually the fingers through this one, and so this actually touches actually that various parts of that oxygenated blood and deoxygenated blood. And when you look at that, say this diagram, so the graph actually you see that deoxygenated blood has the so this dotted line here. So this dotted line has a deoxygenated blood, and deoxygenated blood has a higher absorption at 650 nanometer here, right? 650 nanometer. And this one, okay, deoxygenated blood, okay, this are higher absorption. Whereas, say at 980 nanometer, oxygenated blood has the higher absorption. So this particular device actually gives actually the right. So differentiate actually that absorption behavior of oxygenated blood and deoxygenated blood, and depending upon the healthy and diseased soft tissues, right? So the difference in wavelength of actually 980 nanometer and 650 nanometer induced by this respectively induced by oxygenated and deoxygenated blood, the differentiate either it is a healthy tissues and say diseased tissues, and it will eventually give the oxygen level here. And so the small tiny actually this NAR laser and the tiny LED laser is actually okay, LED, okay, 650 LED and 980 LEDs are in the pulse meter, oximeter here. Okay, the same principle is also useful in a biological application like that. Okay, and so now we move on to that actually bioimaging, how we can use it actually for bioimaging. And so we know actually that say we are using actually various microscope. Say generally biologists use a microscope, and say material science use material scientists use the microscopic technique like FESM technique or say transmission electron microscopy techniques. But for biology, especially for visualizing the cancer cells, we can use actually the conventional, say, a wide field microscope, the conventional microscope that you are using in the lab. And for precise visualization, people are using confocal microscopy. And the more advantageous one is 2-photon microscopy here. That is by using up-conditioned nanoparticles here. Let us have a look on this one. Say this actually, this is the focal point here. This wide focal point here, right? So this sharp focal point here, and this also sharp focal point. But in this case of the conventional microscopy, so because of the wide focal point, then so this gives it an astigmatism, right? From so different cells part here. So this gives actually certain some disadvantages in differentiating actual cells actually, because this gives the small contrast images. Whereas the confocal means then precise actually spot can be actually specifically focused by the confocal point, because by using the shutter mechanism, then only those actually the fine focus point alone go into the cells and visualize this one. Whereas in this case, actually we are using the multi-wavelength here. Whereas in the case of 2-photon only here, only that 980 nanometer is illuminated and then visualized actually by means of only the blue light or the green light here. And because of that, say the green light or the red light actually or blue light emitted by the up-condition, then that has a different advantages. So that shows that the wild field excite a column of tissue section because the emission fluorescence from both inside and outside the focal plane. So this gives out of focus fluorescence. So this will obscure or minimize the depth of tissue imaging. Whereas in the case of the confocal imaging, this is somewhat advantageous. So in the confocal imaging, you see that there is a small pinhole is actually there in the detector, blocks the outer focus light. So allowing only the light in focus, and that is actually collect only from the, say, the cells under investigation. So this improves the, it dramatically improves the visualization details of the certain cells. Whereas in the case of the 2-photon microscopy or multi-photon microscopy, there we are using the up-conditioned particles, and in which actually say delivers light in short, so rapid pulses from NAR range, which penetrates more deeply into the tissues, and hence that gives a reduced photo bleaching, maintain high level of contrast imaging in the case of the, say, that is the advantage of 2-photon imaging by using the up-conditioned nanomaterial. So for high contrast imaging of cancer cells, they are using the 2-photon microscopy based on the upconditioned nanomaterial here. And this illustrate that, say, so this is actually for wide field microscopy, and this is actually for confocal microscopy. This gives a good visualization there. Okay, so I will skip this one because of the limited time. And when you look at that, say the biocell, say most of the biology people knows well, and some of these physics, the faculties, those who are working in a biology, maybe, okay, knows well little bit detail about the cell structure. Then okay, so this is actually, so that in biocell here. So in the biocell, actually you have a larger actually nucleus. This actually in micron scale, right? And around which actually there is a inside this a nucleolus here. Okay, so most of these actually drugs actually go into that say cells, especially these go into the nucleus and nucleolus of that cell, and that actually useful in actually killing the cancer cells, or also in various other say diseases as well here. And apart from that, say the mitochondria is a little bit actually smaller in configuration to that of a nucleus, and other the cytoplasm here. Mostly this particular say nanoparticles when we visualize actually by using the cancer cell, but say the biologists who are interested in a specialized say visualization, then they can investigate how the nanoparticle either into this nucleus or nucleolus or the mitochondria, and depend upon that, say they will use it for the different investigation in that case. But we are limited only with the how our nanoparticle get entered into the nucleus or nucleus, then we correlate actually so for certain bio behavior in that case. Okay, and so this is actually schematic sketch illustrating about actually the upconditioned nanoparticles, right? How it get enters into the say the nucleus, and when these actually NIR actually light is illuminated on that, say, so this nanoparticle go into the nucleus of the cells, and when get interact with the NIR light, then gives the visible light, and this visible light actually, right, kills the cancer cells actually, that, right? And this is actually our we investigate our own material with certain HeLa cells, right, by using confocal microscopy, and this is a kind of HeLa cells, and so this is one other HeLa cell here, and this is actually constructed image of this one, overlapping image of this all these things. When you look at that, say this is the HeLa cells, and this is the nucleus, right, and this is the nucleus, and this entire thing is go into the nucleolus of it. So these small things as particles, these particles enter into the cancer cells. And suppose if you load these nanoparticles with certain drug molecules, we see that so these drug molecules also go into that on actually interacting with the NIR light. So what happened? Then localized induce certain localized heating, and they kill the cell, but as well these also deliver the drug molecules into that. That also so kills the cancer cell. So it acting as a dual role here. So just we wanted to explore about how our particle behave in that case. We didn't go into that because it needs actually a lot of collaboration with the biologist and to know more details about that. Okay, and so I will skip this one because okay, so this also okay, so this gives an okay image about actually that if I illuminate with the 600 nanometer light, and this about 780 nanometer NIR light here. Okay, so this is the kind of actually particle that are loaded with actually that visible dye and the NIR dye here, and and when you look at that NIR dye with the say NIR illumination, then you see that so this is the particle, right? This is not the particle, but this is the say the cancer cell here. So if we visualize by using the visible light, then we cannot able to see that say where exactly the cancer cells is here. But so this NIR light actually induced by this NIR dye is picture out actually the at which exact position the cancer cell is there. Okay, so those actually mice actually that injected with the NIR acting dye is actually useful to visualize these cancer cells. That is the advantage of actually NIR based imaging here. And So another advantage of actually what we discussed until now is actually about the principle of the conduction, then various nanomaterials of conduction nanomaterials, and so how there is energy transfer process involved actually gives the light emission, and also I just wrote about what are various nanomaterial synthesis and cancer imaging, and so these upconduction nanomaterials can be useful for the optogenetics. So it's a quite interesting field. This is the upcoming field here. That is neurophotonics. Okay, this is the comes under the neurophotonics. So suppose if some cancer is there in the skin part, then okay, we can just inject the upconduction nanoparticle loaded with the dye molecule. So very easily, then illuminate with the NAR laser, we can kill the cancer cells. But if some actually the cancer actually tumor, brain tumor, how one can do that? So by using certain, say, certain neuron specific actually that the chemicals functionalize with the upconduction nanoparticle. So once it gets injected into that, these so the nanoparticle go in functionalize around the neurons in the case, right? So around the neurons in the brain here. So when upconduction nanoparticles go around this neuron, and we can actually illuminate actually with the NAR light, because we know that so NAR light is high penetrating power. So these NAR light can be penetrate even to the skull in that case. So these will go into the neurons, right? So this will give certain stimulus action on the neurons here. Okay. So there is a stimulus action of the neurons induced by the NAR light, activated by means of the upconduction light. Then, so the neurons can be activated. Okay. So the neuron gives certain electrical signal in that case. So that kind of activated, new electrical signals are activated by this NAR light is useful to with Alzheimer's disease in America. So most of the aged persons are actually becomes subject to certain various Alzheimer's disease. So அவங்க வந்து எங்க இருக்காங்க எது இருக்குன்னு தெரியாது. அப்போ வந்து இந்த மாதிரி ஒரு ரிசர்ச் அங்க பண்ணிட்டு இருக்காங்க. So optogenetic research, right? And so optogenetics is actually nothing but a biological technique to control the activity of neurons or other cell types that is genetically modified to express the light sensitive ion channels here with certain light here. Okay, so this is the technology that enables neuroscientists to use light to control neurons with high spatial and temporal resolution. So specific neurons in the brain are genetically modified to overexpress with the light sensitive proteins. So when light hits these neurons, the proteins actually neurons are get activated, causing the neurons to get fire. So this gives certain signals, small electrical signals in that case, and so that can actually activate the neurons in the case of the Alzheimer's disease affected person here. So using optogenetic, neuroscientists can precisely measure the effects of turning a set of neurons on or off by means of electrical signals, right, in real-time basis in the case. So they can see the behavior they contribute, allow them to infer to what actually they needed to identify the cells and to contribute to remedy of the disease states. So this kind of optogenetics or neurophotonics by using upconduction materials is to treat the Alzheimer's disease. And this is one article published recently in Science. When you look at that same importance of these optogenetics by using upconduction, so near infrared deep brain stimulation via upconduction nanoparticle mediated optogenetics. You look at these scientists actually, they are from US, right? Megha is US, and the scientist actually Kimura and Tanaka, right, are actually from Japan, and other actually scientists actually from China, and other scientists from Germany, and even some Indians are involved maybe in the yes. So please refer to get more details about the importance of the upconduction material for neurophotonics or optogenetics, like that. Okay, so please refer that. Okay, because of the limited time, then I will skip this one, right? So this is actually the schematic of actually that. So non-invasive therapy here. Let us say that this is non-invasive. Suppose if sometimes actually tumor persons are affected, then they have to operate the brain surgery like that. This is very tedious, right? So, okay, so people are thinking to use this. So maybe in another 10 years, I don't know, in 5 years. So this may come into the picture in, say, various hospitals for this tumor treatment, brain tumor treatment. And obviously the photodynamic therapy, as I explained before, so we can load this particular so upconditioned nanoparticles with the dye molecules, and once actually the upconditioned nanoparticle illuminate with the IR laser, then gives visible light, and so this upconditioned nanoparticle actually visible light, actually green light or red light in the case, and so these are dye molecules there. So the upcounted green or red light actually get absorbed by the dye molecules and that go into the higher energy state, say, then release a certain redox oxygen species. So when it releases the redox oxygen species around the cancer cell, then it actually kills the cancer cell here. So one advantage is that, say, the localized heating induced by this IR laser and the redox reactive oxygen species here. Both these are responsible for this photodynamic therapy. I don't want to go much details in that. So even people are using for non-invasive surgery as well for these, right? The upconditioned nanoparticles here. Okay, so let us have a look on that. Image guided cancer surgery using near infrared fluorescence by using the upconditioned nanomaterial here. Okay, so how actually that say the nanoparticle get injected into that, right? And they illuminate with a certain NAR light. So you know that as we just demonstrated, how when we illuminate the upconditioned nanoparticle with the NAR light, that gives the green emission there. So like that, when we inject this upconditioned nanoparticle and illuminate with the NAR light, LED or laser, then gives that small signals. And so these signals can be visualized by using the NAR camera. So this actually helpful in actually surgery here. So image guided cancer surgery by using this upconditioned nanomaterial. So by using these actually various examples, we may be able to understand that the importance of the upconditioned nanomaterial for various biological applications like that. Okay, so I will skip this one. Okay, so there are various. I will also skip this one, right? And we also use actually nowadays actually we are working on previous student Anbarasi. He has worked in loading these upconditioned nanoparticles with a certain turmeric actually. She has prepared actually curcumin from turmeric and then loaded that nanocurcumin with the upconditioned nanoparticles, and we investigated this how these nanocurcumin loaded upconditioned nanoparticles is useful to treat other cancers. In this case, we did this work in collaboration with the Russian scientists through our Indo-Russian project, and so we synthesize this material by using that say micro emission method, and we are able to get actually the blue emission by using the ytterbium thulium, and this is actually ytterbium erbium thulium nanoparticle. Then we functionalize with the say polymer mud, that is PLGA, because we tried to actually made it as a water dispersible one, but slightly it become water dispersible. And then we also sensitize with a certain nanocurcumin. This nanocurcumin not only acts as a herbal drug, but as well is also acting as a say dye molecule here. So we can use it actually even for the photodynamic therapy, and with the help of the Russian scientists, we just use these studies, and we understand that actually these nanocurcumin loaded so upconditioned nanoparticle enter to that say the specific cancer site, and this is actually interacted with the say NAR light. So we are able to synthesize this upconditioned material loaded with the nanocurcumin herbal dye molecules to eventually useful in go into that of a cancer site, and also is useful to treat somewhat actually the cancer. And this work is still under say undergoing that case, right? And she also actually functionalized these upconditioned nanoparticle with the doxorubicin drug molecule, and this work is also under progress for our in vitro and in vivo studies here. And presently another student who demonstrated. So now Ajit Kumar, he is working on photodynamic therapy here. Okay, so So there are actually, we demonstrated various applications of our nanomaterials, of conditional nanomaterials with the different, say, application like that. And apart from that, we also use it for the, say, optical trapping studies in that case, right? Okay, so, okay, these are the simple explanation about actually nanothermometry. So this nanothermometry is another application like that. Say, this actually we are using dual laser power here. So one is actually 738 laser and 980 nanometer laser. And when we actually dope the same, say, sodium yttrium fluoride or sodium lutetium fluoride, so with ytterbium, erbium, or we functionalize with some other material that can absorb the 980 not only 990 nanometer, but as well that absorb the, say, 800 or 850 nanometer laser here. So there's a dual activation of a, say, NAR light. So it increase the potential of the drug release and as well increase the potential of actually photo thermal therapy and the photodynamic therapy. So these are the various actually. So these, when you look at that, these are nature communications. Okay, so you can understand that importance of this material for various applications. And this particular, say, the video shows that actually. So this is actually of a cancer cell, and this is actually a, say, nanoparticles. Say this one, these nanoparticles get enter into that, right? So like that, what happened? We can load this doxorubicin nanoparticle with the upconditioned nanomaterial. So what happened? This upconditioned nanoparticle carry this drug and specifically go into that cancer cell. So by activating with the NAR light, that can deliver the drug molecule into the cancer cell. So it will be able to cure the cancer cells. This is one type. And as I point out, when you put the dye molecules, we can inject actually the photodynamic therapy like that. So many behaviors we can using this one right here. And so when we actually drug release behavior of a doxorubicin loaded upconditioned nanoparticle, then you see that, okay, so this gives actually the 730 nanometer laser, then gives actually heats up, say, the 42 degrees Celsius around. So this much of a, okay, 41.5 degrees Celsius get generated by the illumination of the dual activation of the laser, and that also with just 50 milliwatt per square centimeter laser, small power laser, it's sufficient enough. So that induce a high temperature about, not high temperature, temperature about 42 degrees Celsius, that enough to kill the cancer cells here. Okay, so there's a photodynamic, photothermal therapy, targeted drug delivery, all these can be combined. So we can make this upconditioned nanoparticle multifunctional platform for photodynamic, phototherapy, and okay, targeted drug delivery method like that. So like that, okay, so many things are that. So then we can use it for the biosensing application. So this is actually that nowadays actually this is the COVID, and maybe around 1.5 years before we have struggled with the testing with the COVID, right? Because we have to go to actually that so corporation office or hospitals to get actually so tested by PCR testing. But nowadays actually we have that the simple rapid testing kit on that. Okay, so this actually lateral flow assay sensor. Okay, LFA sensor. Let us say that it is lateral flow assay sensor. So these lateral flow assay sensor is actually generally so useful for various diseases. For example, pregnancy testing or other, say, tuberculosis testing. So but regarding this COVID, actually there is not much actually the things have been happened, but only in recent times actually. And you see that so we bought about 10 actually. My wife actually recently got affected with the COVID, and immediately she ordered for about 20, right? The lateral flow sensor. But say, what is the things involved in that lateral flow sensor here? Let us have a look on that. Say, when you look at this run, so this is actually for in lateral flow sensor, say sensor. Let us say that this is the okay sample cavity. Then the okay, so this is the testing, and this is actually the same. Okay, this actually through the membrane activity that goes. Let us see that this happens. This one, right? So this actually we can be the same upconditioned nanoparticles have been used for the HIV testing like that. Okay, so this is actually lateral flow assay sensor. And in the lateral flow sense SR, there is a sample pad and a conjugate pad. There's a test line and the control line, then absorbent pad. The same things actually involved in the, say, the COVID rapid testing lateral flow sense SR. But depending upon the kind of viruses and kind of actually is in that, then that is actually functioning within antibodies. Then, so say for example, in the case of that HIV testing, then they have, okay, the functionalize these subconditional nanoparticles, right, with certain HIV-1 activated antibodies here. So this one is actually a test line and another one is the control line here. And when actually these HIV affected persons actually that say is put in this particular sample slide and then get illuminated with a certain so illuminated then this actually this functional with the upconditional nanoparticle. When it's illuminated with the 980 nanometer, so once actually the test line is there, when is the HIV tested person is there, then that gives actually the green signal in that case. So that gives actually evidence for the presence of the HIV like that. So even in the case of say so kit actually the fast array kit fast kit in this case, if the test line shows certain marking, then say the person is actually diagnosed to be a COVID affected person, COVID positive like that. The same way upconditional nanoparticles are also nowadays useful for say detecting various diseases by using this say lateral flow sensing lateral flow assays. And so what is the another thing is that say nowadays actually mobile phone integrated say the lateral flow sensors are LFA lateral flow assay sensor here. Okay, and you see that actually the same kind of actually the sample pad and say the test lines and the control line, these are all okay functionalized with certain say antibodies associated with certain diseases. And so these are with certain primary antibody and secondary antibody here. And so when a laser diode actually illuminate the test line, then if it gets affected and this activate these molecule to emit the light, so this will get actually detected. And so this is actually by using the say the simple cell phone itself, one can able to transfer this actual data, and through the cell phone one can transfer the data to the doctor, and the doctor can actually transfer that actually test data to directly to the patients actually. So these are advantage. These are the things that coming up nowadays by using the upconditional nanoparticle based the flow sensor. And so another thing is that actually the upconditional nanoparticles are also useful for say so biosensing here, food quality. Okay, so what we've seen is actually how upconditional nanoparticles have been used actually for various kinds of cancer imaging, cancer photodynamic therapy, photothermal therapy, and also seen about how it is useful for nano optogenetics and neurophotonics. Then now we are using actually we can use it also for the biosensing, as I previously just explained about for rapid testing of the disease by using LFA sensor here like that. So one can use this upconditional nanoparticle for sense biosensing of the food and to test the quality and the safety applications of that one. Okay, and see the foodstuffs actually mostly contaminated with certain fungus. So that is what you call the mycotoxins. Okay, so almost all these actually the cereals actually like that of a corn, wheat, or so many food material, peanuts, and if it is stored with a certain moisture, right? So this always gives such a kind of the fungus. That is so toxic the fungus. Even the bread mostly affected the bread. So how to visualize actually how to so identify even if it is actually microgram level or in ppm level here. So in that case actually that upconditional nanoparticles have been used, right, for sensing these that acrotoxin molecule here. So this is actually another kind of a rapid testing kit, and this rapid type testing kit actually functionally is suitable, say, upconditional nanoparticle, right? So these upconditional nanoparticles actually the functionalize with a certain suitable, say, DNA, cDNA. I don't know much details about that. Okay, only to make to get interest on this aspect only, I just put in this. So various biomolecules like that actually functionalize with this say conditional nanoparticle. Then they put in that certain test line or the control line in that case. Then they extract actually this kind of oxodiractin induced from the food molecules, then inject into that, say, the sample pad, and once it get illuminate with that, say, so this actually, the negative means actually that say test line both actually give the emission, whereas if it is positive, say it would get illuminated, then the absence of this light, by which one can able to see actually how, right, one can use the conditional nanoparticle for the biosensing of this one. So nowadays actually people are using various kinds of plasticizers in various products. Sometimes actually these microplastics actually get embedded into these food products. So these kind of microplastics also can be detected, and some literatures are also there actually by using the conditional nanoparticle like that here. Okay, and so just I copied this from Journal of Food and Composition Analysis, and if you look at this, the development of bimodal sensor based on conditional nanoparticle surface and Raman spectroscopy for the sensitivity determination of the say dibutyl phthalate in food molecules like that. So we have actually shown actually various examples of conditional nanoparticles for okay that, and we have also demonstrated actually even for the solar cell application. Then so out of scope of this thesis, out of scope of this particular right talk, but however one of my students has worked on that, and we are able to just give certain little bit incremental say improvement in the efficiency, not that much of high efficiency, but only certain little bit of high efficiency, little bit incremental efficiency only. For example, in the case of the high sensitivity solar cell with the nano TiO2, that gives 6.9%. But when we actually have the equal composition of a barium yttrium fluoride doped ytterbium verbium with the TiO2, then the efficiency is about 7.6. But even later, we investigate with the various compositions of the TiO2 with the different conditional nanomaterial. We have collected and okay about nearly about 9% efficiency of that. Okay, still we are not yet published this work, right? And so we can able to use even dye-sensitive conditional nanomaterial for dye-sensitive solar cell. Okay, like that. And so this actually right. So with this actually I am nearly at the conclusion stage, and we have prepared so many actually materials, and we also pointed about actually condition the principles, various condition nanomaterials, and what are the various nanomaterials we have synthesized, and what are the various nanomaterials of condition have been functionalized the different dye molecules for photodynamic therapy, and there is different biological applications like that. So with this I wanted to conclude, and so because this particular is attended by most of the faculties, so please actually note this actually website actually. This gives a simulation of various spectroscopic and various demonstration of the physics experiments. So you can refer this website to our students, right? So with this actually I wanted to conclude, and so the thing is that actually, so the first one actually is opened with the Tiruchirappalli, and finally, so the awares. So the sayings actually that, so we know that actually Totanitur Manakani, like that here, Varapuyera, Neer Verum, Nel Verum, Kudi Verum, Coal Verum. So the thing is that actually I wanted to say that Professor Jafar sir and Professor Gunasaran sir and the entire actually the physics department of Jamal Mohamed College actually made a wonderful opportunity for all the faculties actually through this say faculty development program to acquire knowledge. So we actually, I just understanding about the conditional materials actually by myself and through my students, I learned a little bit, and so I transfer this knowledge actually to all the faculties. So you please actually transfer this knowledge to our students, and you can also work with this kind of materials. So as a whole, as a teacher, we transfer the knowledge to the student and let the students to grow up in their life. So this is the concept of actually my visualization regarding this awareness, this particular thing in that case, right? So So like the same thing is applicable to our, suppose the institute wants to develop, so the students and teachers and all the faculties should work hard actually to develop actually that colleges. If all the colleges in Tamil Nadu, okay, so flourish, all the universities flourish, then Tamil Nadu will become a top in the India. And if all the universities in India, then in India actually we can do a quite lot of actually knowledge to the world. So this is the concept we have to take in positive ways. So you please actually take up certain knowledge of this subconduction material, those who are interested and work. And if you have any doubt, actually, please clarify either through this talk or through by email. I always actually support actually regarding this kind of work. So you can do this kind of in our laboratory in the case. Okay. So thanks actually for the opportunity given by the Jamal Mohamed College, Professor Jafar sir, Professor Gunaseran sir, Professor Anbadagan, and all the faculties and the management of Jamal Mohamed College. And absolutely, I should thank actually all the audiences, all the participants of same for the patiently listening to this lecture. Maybe it's about 1.5 hours. So I think it's quite hard, but however, so I think it may be certain interesting. You might be take certain interesting aspect from this talk. And apart from that, I thank actually my research students, Dr. Gunasilan, Dr. Arun, Dr. Yamini, Dr. Anbarasi, and Mr. Ajit Kumar, who recently joined. I also collaborate with the certain professors in US and also thank them, Professor Gangadhan from University of Texas, Professor and Henry from Moscow Medical Universities, and other collaborations actually from Sri Siva Kumar Mahalim. So without collaboration, okay, so it is not at all possible this one. So regarding the bioapplication, so if you want to do this kind of material science aspect, no problem there. So you can synthesize, you can investigate by using the various facilities available in either universities or in our colleges or by collaboration with some other faculty. But regarding bioapplication is concerned, absolutely we must have to have a collaboration with the biologist. Okay, either we can use it for the biomedical application or for solar cell application, or depending upon your interest, you can take up this work and flourish well. Thanks a lot for all of you. Thank you, sir. Thank you, Professor Jafar, sir, again.
Thank you, sir, for our nice presentation. You have explained the detailed information about photon upconversion nanoparticles. It was very useful, sir.
Chat box.
Dear participants, it is a time for open discussion. So do you have any questions, any clarification? You can ask our resource person.
Sir, Senthil Silvan, sir.
Sir.
Sir, I am Radhakrishnan, sir, Jamal College professor. I am working here, sir.
Yes, sir, please, sir.
Sir, you are talking about the upconversion.
Yes,
sir,
sir, yes.
Susceptibility tensor nature of that material, how does it differ from non-curved materials, sir?
I'm not able to hear it voice properly.
Sir, how does it differ from the non-curved material? What is the nature of the susceptibility tensor of this upconversion material, sir?
Susceptibility mean to which property susceptibility do you mean?
All are due to nonlinear property. Okay, sir. What is the reason for this kind of energy upconversion, sir?
So, sir, actually, as I pointed out before, actually, so this is energy transfer upconversion. So actually, we are using two different actually ions like that ytterbium and erbium. So ytterbium has 2 levels and erbium has many levels. So what happened? This is not like actually nonlinear. Although it is a nonlinear optical process, but so this is not actually induced by virtual energy state as involved in second harmonic generation. So in the second harmonic generation, there is a virtual energy state is in that. So very high pumping power is required. So in the case of second harmonic generation, then there is a polarization of atoms involved. In order to polarize the atom, absolutely we need to have a very high monochromatic light of a high intensity to have very high electrical field strength. But in this case of upconversion material, so this is not depends upon the polarization of the molecules. This is depends upon only the energy level, say transfer from one ion to the other, as well the energy level, energy transfer from one ground state to the other excited state and another excited state say other higher excited zone. So here up conversion is related to that of a say energy transfer up conversion.
Upconversion is a linear property, sir. It is not a.
It's a non-linear property. It is a non-linear property here.
Then what is the non-linearity, sir, working here, sir?
So here non-linearity is related to the energy transfer process here. So there is no such virtual energy transfer here.
Energy is related with then automatically polarization but it is not like that.
Yeah, it is energy is in the case of the organic molecule. So like that of a potassium dihydrogen phosphate. So in the case of organic molecule, then so nonlinear optical process is associated with the right. So associated with the polarization. But in this case of conversion, even though it is nonlinear, so we are not making the molecule to get polarized, right? So here, not only there is no necessity to have the molecule to get polarized regarding the upconversion in a material is concerned. So no polarization is involved in this.
My question is the upconversion property is here nonlinear property. Now, how this nonlinear property is induced in the material, sir? If you told that it is not related with the polarization, because from my understanding, the nonlinear optics comes from the susceptibility tensor. If the first order not is linear material, if the second order susceptibility, third order susceptibility are not zero, then nonlinear.
Okay. You mean actually that kind of susceptibility, but here there is no susceptibility sensor is involved here.
So then how does you define your nonlinearity here, sir?
So that is as I pointed out actually before. So the nonlinearity is actually related to that of say the NIR excitation. So these NIR excitation transfer the energy, right? So in the case of the simple harmonic, second harmonic generation, then the light is actually transfer the energy to the molecules to get polarized, right? But here the energy is actually make the molecules not to get polarized, but make the atoms actually transfer from one energy state to the another energy state. Okay, so in this case, we cannot actually confuse with the state of polarization of the molecule. So as we take the examples of second harmonic generation and upconversion, in the case of second harmonic generation, so in order to make the polarization, then we need to have a very high energy. But in this case of upconversion, the energy transfer is there. Energy transfer is not in terms of polarization of the atom, but in terms of transferring the energy from one atom to get transferred to the other atom. So this is the thing that involved in this upconversion.
How does upconversion material differs from the current material? That's a second harmonic material you are telling. That is point is very clear to me, sir. What is my question is then what is the reason? What is the reason for this kind of energy? What is the physics? How do you define the role of nonlinearity in this material?
Say, for example, in the case of the KTP crystal, so only that potassium dihydrogen phosphate is also involved, right? So this is organic crystal, right? Is it? This is it is not a nonlinear optical crystal, right? Okay. Is it? Whereas in the case of the what we experience, what we have experimented, mostly related to the lanthanide based material. Okay. We always work upon this energy transfer based on the say lanthanide material. So we always use this ytterbium, then with the erbium or thulium or holmium here. So the basic difference between the material concerned in second harmonic generation is say not a lanthanide doped material, but we always consider about certain organic crystal. Right, so this is one different aspect. Whereas in the case of upconversion material, even though we can use the crystal, but it's not an organic crystal, but we always use the inorganic crystal that based on the say certainly lanthanide energy levels. So when we correlate the physics of actually that of same the nonlinear optical physics of upconversion material, say we have actually the ladder-like energy levels. So in order to have the energy transfer of conversion, in order to have the excited state energy transfer of conversion, we need to have a certain material to be doped with certain ladder-like energy levels. So mostly these lanthanide materials have the lanthanide energy levels. So these obviously gives efficient energy transfer process. Whereas in the case of second harmonic generation, only the we no need to have a it is a two different entity of the material.
Okay, sir. Sir, excuse me, sir.
Yes.
Sir, the purpose of my question is, sir, I am working in the field of optical solitons, sir. I am student of Professor Lakshman, sir. I am working in the field of optical solitons.
Good name, sir? My
name is Radhakrishnan, sir.
Okay, right.
I know you, sir, personally. We are meeting when I am doing the research. I came to your room. I am a student of Gopalakrishnan, sir. I am friend of Gopalakrishnan and Amudan. On that
Okay,
basis.
okay, right. Good.
I came to your, I have stayed your room, sir.
Oh.
When I am okay, at the age of, I came to the Nano city, and at that
Okay,
time I met.
okay, right, nice, okay.
Sir, that what is my question is because where we are deriving a mathematical model from certain nonlinear property, we are deriving the mathematical model for Kerr material and non-Kerr material, sir. And we are studying how the light waves are propagating in a fiber and like that. So like the, what is the then mathematical model for this? What is the new material you are telling is? What is the mathematical model? How one can obtain it? What is the basic birth of nonlinearity? That is my asking, sir. If I know the basic birth of nonlinearity now, from that equation, shall I find any dynamical model for your energy light propagations in your material? So in what?
Yeah, okay. Very good question, right? Same. So we are not involved in a theoretical modeling of that one. So we actually materials modification and material science oriented thing only. So we didn't investigate any dynamics of actually say unconventional light emission. We didn't investigate the theoretical phenomena behind this one. So I'm not able to give a good answer regarding the theoretical. But I find actually mostly as I worked in related to the experimental side, I just focus on my thing. But I know actually some finite difference, time difference simulation, no? FDTD like that, right? So they are using some softwares actually that. Okay. But I'm not sure about which software is specifically used for this investigation, theoretical, so dynamics of this one.
Okay, sir. But what all the energy level diagrams that you are seeing is the simulation output of the simulation, sir? Or
no, it is not actually here, simulation here.
It is the experimental observation, sir, the energy level diagram.
Yeah, okay. All the energy levels are associated with the energy, so it is not the simulation here.
All are experimental observation.
So it is actually inherent property of the material behavior various energy levels. Right?
Your diagrams that you are getting from your experimental, okay, sir? What you are showing in the diagrams.
So this is actually used the standard actually energy levels of so various lanthanide materials.
Okay, sir. Useful energy level material. Okay.
So these are all various standard energy levels of that one.
Okay, sir. That's right.
Suppose if you look at the lanthanide energy levels, you can see that. Okay. So we just use these standard energy levels available in the book, and then we explain the energy transfer process.
Because of the doping, how the energy levels are changing, that you are saying, sir. Because of the doping, how the energy levels are changing, because of the change in energy level, and
no, here there is no energy levels is not actually the changing. So we are using actually, say for example, in the case of that material ytterbium, erbium. So ytterbium has actually only two energy levels, right? So the energy level shifting is not occurred here. Okay. So in the case of the erbium also, the energy level positions are the same here. Okay, we are not worrying about the energy level shifting in this, say here. So for example, 20% ytterbium that has the same energy level. So these energy levels does not get shifted, right? Okay. So in erbium also there has a different ladder like energy level. So there is no energy level shifting. We are not considering about the energy level shifting in this case. So even though we are doping actually the small percentage of that one, so we didn't see about actually energy level shifting in this case, right? So what happens, only we are understanding about how the close proximity of these two such a sensitizer and activator ion here. So depending upon the dopant concentration, then that will affect the closeness of the distance between the proximity of the distance between these, so ytterbium to erbium. So the energy transfer is actually related by this, okay? So energy levels, inherent energy levels. And there is no such energy shift is occurred. So almost all these say what is that energy? Yeah, a DR spectrum or say emission spectrum. So we didn't notice that one. If there is energy shifting, then obviously we see that say we are not able to get actually. We will not be able to get actually that much of unconventional emission in the green or red. So we are very sure that there is no such energy shifting happened by this doping.
Okay. Thank you, sir. Thank you for your clarification, sir. I am very grateful to you, sir.
Thank you. Put a lot of clarifications. Very nice actual interaction. So any more questions? The chat box.
Thank you, Dr. Senthil Salvan. Thank you.
Thank you, Professor Jafar, sir. Thank you. Thanks for motivation. Right?
Nice. It is because just you said that the participants level will be that much. Of course, you have managed everything. Nice it is. Thanks for your nice presentation, and the information is given to the doubts raised by the people, and the topic really the photon upconversion nanomaterials will be an eye-opening for the people who are going to work in this particular field. Where, of course, with the starting from the fluorescence, luminescence, and all these things, just I entered lasers, and really it was an eye-opening for the people who are going to enter into this particular field. Thank you, Sendil sir, for coming along that. And of course, among the disturbances you had already, I know pretty well. We pray for the recovery of your wife soon. We all the participants, we pray for the quick recovery of your wife from corona.
Thanks a lot for praying. Okay.
Yes.
So,
in spite of all the disturbances you came all along the way, I first thank you for this regard, because when she is in hospital, just you have spared the time to come to the department, and you spare the time with everyone, and you clear the doubts without having any disturbance. Just you have explained everything. First, we thank for your commitment, because you already committed that you will be coming. Of course, you have fulfilled that promise. Thank you first, and we all the participants and our department people, we pray for the quick and safe recovery of your wife soon, and she'll be coming to your home soon. Thank you.
Thank you, sir. Thank you, sir. Actually, one more thing. So several participants have put some questions, so I don't know how to answer for all the things. And one interesting question is that
they will be sending. They will be sending to the mail, your mail, and of course you can post them in that regard. If they yes, they will call you back. Just through mail, they will contact you. Okay.
Okay, sir. Okay. So once again, I thank the management and authorities of Jamal Mohamed College, and of course, actually, I should thank Professor Jafar sir for so over this. Actually, this gives a wonderful opportunity for me to interact with you. So we speak a lot actually for about say how about hardships we have faced during our PhD time. And this gives actually constancy and confidence to our levels. And
yes.
So, and as well, Dr. Ebenezer, please convey my regards to Dr. Ebenezer as well, and all our faculties. And once again, I thank Professor Gunasaran sir actually for giving me this wonderful opportunity through you to give a talk. And so all the faculty, I thank all the faculties and all the participants especially. Thanks a lot, sir. Thanks a lot.
Thank you, Sandil. Thank you. Have a nice time. Take care of your wife and take care. Of course, tomorrow the program will be starting by 9:30, and the people concerned will be having that. And you can also have a glance on it, and you can pass a comment over that, Sandil. Take care.
Okay. Thank you.
Thank you. Thank you. Thanks for all the participants who have spared their time for this program. And tomorrow we will be having once again a glance on this particular topic. Jamal sir. Arivalan sir, just will be having the resource with them, and then they will be sparing that idea for you people. So the participants, please come over here, and after crossing 100, this it will be diverted to YouTube. Just you can have a glance on YouTube also. Thank you, and once again, thanks for everyone, and we thank Almighty for the successful completion of the first day of the 2-day program. Thank you once again for the people who have spared their help in every dimension for the completion of the first day. Thank you, under all. Thank you.
Okay.